Have you ever looked up at the night sky and felt that tug of something bigger, something hidden? The universe, for all its breathtaking beauty, keeps its deepest secrets locked away, whispering hints through phenomena we're only just beginning to understand. We see the stars, the swirling galaxies, the silent dance of planets, but what we don't see are the invisible hands guiding it all. Think about dark matter, that mysterious substance that makes up most of the universe's mass yet slips through our finest instruments completely undetected. Or quantum entanglement, where particles millions of light years apart communicate instantly, defying everything we thought we knew about time and space. These aren't just scientific curiosities, they're clues, pieces of a cosmic puzzle that's been waiting for us to put it together. Behind the scenes, hidden forces are at work everywhere, from the gentle but relentless pull of gravity to the mind-bending possibilities of string theory, where reality itself might be woven from vibrating threads too small to imagine. It's almost like the universe is playing by a set of invisible rules, and we're only just learning how to read them. These forces don't just shape galaxies, they shape reality as we experience it, dictating how matter behaves, how time flows, and perhaps even how consciousness arises. What if I told you that some of the greatest minds in history have been quietly chasing these mysteries, proposing theories so wild and wonderful they sound more like science fiction than science? Theories that suggest we might be living in a multiverse, or that dark energy is slowly tearing the fabric of space itself apart. In this video, we're diving deep into 30 of the most incredible theories about these hidden forces, ideas that will stretch your imagination and challenge everything you think you know about the cosmos. We'll explore how something as seemingly simple as gravity might be leaking into our universe from another dimension, why empty space isn't really empty at all, and what it might mean if we're all part of a cosmic hologram. This isn't just a list of facts, it's an invitation to wonder, to question, and to see the universe in a whole new light. So settle in, open your mind, and get ready for a journey to the very edges of understanding, where the questions are as thrilling as the answers. Let's begin with a theory that asks a radical question. What if one of our most trusted scientific laws is simply incomplete? For centuries, Newton's laws of motion have been the bedrock of physics, perfectly predicting the behavior of objects from falling apples to orbiting planets. But when we look out at the vast, spinning pinwheels of distant galaxies, something strange happens. The stars at the outer edges of these galaxies are moving far too quickly. According to Newton's laws and the visible matter we can detect, these speeding stars should be flung off into the void, yet they cling to their galaxies as if held by an invisible hand. The prevailing solution to this mystery is dark matter, an unseen form of matter that provides the extra gravitational glue. But another idea, born in the early 1980s, offers a dramatically different approach. It's called modified Newtonian dynamics, or MOND, and it was proposed by physicist Mordechai Milgrom. Instead of inventing a new, invisible substance, MOND suggests that our understanding of gravity itself might need a tweak, but only at the most incredibly tiny accelerations, the kind found in the vast, sparse outskirts of galaxies where gravity is almost imperceptibly weak. Milgrom's insight was that below a certain acceleration threshold, gravity could behave differently than Newton or even Einstein predicted. It's not that the laws are wrong for everyday life, but that they might not tell the whole story in the most extreme environments. When this modification is applied, the math of MOND can perfectly reproduce the rotation curves of many galaxies without a single particle of dark matter. It's an elegant solution that does away with the need to find something we've never seen. The evidence for MOND is compelling in certain arenas. It has had remarkable success in predicting the motions within a diverse array of galaxies, often with more precision than some dark matter models can muster. For its supporters, MOND represents a beautiful piece of physics, a simple modification that solves a complex problem without invoking the unknown. However, the theory faces significant challenges. While it excels at explaining the behavior of individual galaxies, MOND struggles on larger cosmic scales. Observations of colliding galaxy clusters, like the famous Bullet Cluster, show a clear separation between where the visible matter is and where the majority of the gravitational mass resides. This is incredibly difficult for MOND to explain without some form of unseen matter. Furthermore, the precise cosmic microwave background, the afterglow of the Big Bang, fits perfectly with the standard model of cosmology that includes dark matter, creating a formidable hurdle for any alternative theory. This leaves us with a fascinating standoff. Is the universe holding onto secrets in the form of invisible particles, or are we on the verge of a profound rewrite of the fundamental forces? MOND forces us to question our assumptions and reminds us that even our most cherished laws are always subject to deeper scrutiny. While MOND challenges our laws on a galactic scale, another theory aims to rewrite the rules for the very smallest pieces of reality. To appreciate its elegance, we first have to understand a fundamental split in the universe. On one hand, we have the particles that build everything we see, quarks and electrons, known collectively as fermions. And on the other, we have the particles that carry the forces between them, like photons and gluons, which we call bosons. These two families are governed by completely different sets of rules, and this divide is one of the biggest headaches in modern physics. Supersymmetry, often called SUSY, is a breathtakingly beautiful proposal to heal this rift. It suggests that this fundamental division is an illusion. The theory posits that for every known particle in the universe, there exists a hidden, supersymmetric partner. An electron would have a partner called a selectron. A quark would be paired with a squark. The photon would have a photino. In this perfectly symmetric view of reality, the fermions and bosons are two sides of the same coin, connected through a deep, underlying mathematical harmony. The implications of this are profound. First, SUSY provides a pristine candidate for dark matter. Many of these superpartners would be stable, electrically neutral, and would only interact through gravity and the weak nuclear force, exactly the properties we've been searching for. The lightest of these superpartners could be floating through you right now, a vast, unseen ocean of matter holding galaxies together. Secondly, supersymmetry solves a major problem with the Higgs boson. The math behind the Higgs suggests its mass should be enormous, driven to incredibly high values by quantum fluctuations. SUSY elegantly cancels out these fluctuations, making the Higgs mass we actually observe, and by extension, our entire universe theoretically possible. Perhaps most compellingly, SUSY allows for the grand unification of forces. At the high energies present in the early universe, the electromagnetic, weak, and strong nuclear forces appear to almost, but not quite, merge into a single superforce. SUSY extraparticles adjust the math perfectly, suggesting that in the first moments of the cosmos, all forces were truly one. For decades, physicists have been hunting for evidence of these superpartners. The primary tool in this search is the Large Hadron Collider, which smashes protons together at nearly the speed of light to recreate the conditions just after the Big Bang. The hope is that in these incredible collisions, energy will momentarily coalesce into a supersymmetric particle before it decays back into the familiar particles we can detect. It's like listening for the echo of something invisible. So far, the superpartners have remained elusive. The LHC has not yet found direct evidence for SUSY, which has forced physicists to push the expected masses of these particles to higher and higher energies. This doesn't kill the theory, but it does challenge its most simple and elegant forms. Some researchers are exploring more complex versions of supersymmetry, while others are beginning to wonder if nature's beauty might be more subtle than we imagined. The pursuit of SUSY is a testament to our desire to find order and symmetry in the heart of nature. Discovering even a single superpartner would be a revolution on par with the discovery of the electron or the Higgs boson. instantly opening a vast new realm of physics to explore and finally revealing one of the universe's most hidden forces. Now, if supersymmetry hints at a hidden mathematical order within the universe's laws, our next theory questions the very nature of reality itself, suggesting that everything we perceive might be an elaborate illusion. This is the holographic principle, and it's one of the most profound and disorienting ideas in all of physics. It proposes that our seemingly rich three-dimensional universe, with its galaxies, planets, and you watching this video, might actually be a projection of information stored on a distant two-dimensional surface. We are, in a sense, living inside a cosmic hologram. The seeds of this astonishing idea weren't sown in the study of galaxies or the quantum void, but in the seemingly paradoxical nature of black holes. In the 1970s, physicist Jacob Bekenstein made a startling realization. He proposed that a black hole's entropy, which is a measure of the information or disorder contained within it, is not proportional to its volume as you might expect, but to the surface area of its event horizon. This was a radical departure from conventional thinking. It suggested that all the information about everything that ever fell into a black hole could be entirely encoded on its two-dimensional boundary, its surface. The work of Stephen Hawking on black hole radiation only deepened this mystery, creating what's known as the information paradox. If a black hole evaporates, what happens to all that information? The laws of quantum mechanics insist that information cannot be destroyed. This is where physicists Gerard T. Hooft and Leonard Susskind entered the picture. They took Bekenstein's idea and ran with it, proposing that this wasn't just a quirky property of black holes, but a fundamental principle of the universe. If the information within a volume of space can be described by what's happening on its boundary, then perhaps the three-dimensional world we experience is not the most fundamental reality. It's a projection, much like the three-dimensional image you see on a credit card hologram. That shimmering bird or globe isn't actually in the card. It's a representation of information etched onto a two-dimensional plastic film. Tilt it and the image moves, but the source data remains flat and fixed. The holographic principle argues our universe operates on a similar, albeit vastly more complex, scale. To grasp the sheer strangeness of this, consider your own body. You feel solid and three-dimensional, but according to this principle, every piece of information that makes you, the memory of your first kiss, the color of your eyes, the structure of your DNA, could theoretically be encoded on the outer surface of the universe. We are not just in the universe is, in a way, happening on a screen we cannot see. This idea forces a complete rethinking of space, time, and information. It suggests a deep and fundamental limit to how much information any region of space can contain. There's a finite amount of data that can be stored in a given volume, and that limit is defined by its surface area, not its depth. It challenges our most basic intuition that more space means more room for stuff. In a holographic universe, the richness of reality, from the spin of an electron to the birth of a star, is all happening on a vast cosmic film reel at the edge of everything. While the mathematics behind the principle is robust and continues to be a major area of research in string theory and quantum gravity, direct experimental evidence remains elusive. Scientists are, however, looking for potential signatures. Some are analyzing the cosmic microwave background for imprints of this underlying holographic noise, while others are using precision instruments to see if there's a fundamental graininess to space-time at the tiniest scales, a pixelation that would be expected if our reality is indeed projected. The holographic principle remains a powerful, if unproven, framework that stretches our understanding of existence to its absolute limit, suggesting that the deepest truths of the cosmos might be written on a surface we have yet to find. If the holographic principle makes you question the nature of your reality, then our next theory will make you question your place within an infinite sea of possibilities. We're venturing into the many worlds interpretation of quantum mechanics, a concept that transforms every tiny event into a moment of cosmic creation. At its heart is the famous measurement problem. In the quantum world, particles exist in a blur of potential, a superposition of all possible states until the moment we observe them. It's as if a flipped coin is both heads and tails while it's in the air, only deciding which side is up when it lands in your hand. The prevailing Copenhagen interpretation says this collapse into a single state is a fundamental random process. But in 1957, a young physicist named Hugh Everett offered a far more radical solution. The coin never actually lands. Everett proposed that there is no collapse. Instead, every possible outcome of a quantum event does happen. The universe doesn't choose, it branches. At the moment of measurement, the entire reality splits into multiple, equally real versions of itself. In one universe, you see the coin land heads. In another, an identical version of you sees it land tails. And this isn't just for coins or particles in a lab. This branching happens for every quantum event, everywhere, all the time. Every time an electron changes its energy level, every time a photon reflects off a surface, and every time you make a decision, a new universe is created. This leads to a truly staggering conclusion, an infinite multiverse, a vast, ever-expanding tree of reality where every possibility is realized. There's a universe where dinosaurs never went extinct. A universe where you took that different job. A universe where the laws of physics themselves are slightly altered, making stars burn out instantly or life never forming at all. In this view, the cosmos is less a single entity and more a sprawling tapestry of every story that could ever be told. The implications for our understanding of existence are profound. It offers a clean, elegant solution to the measurement problem without needing a special rule for observation. It also provides a fascinating, if unsettling, perspective on identity. The you in this timeline is just one version of countless others, each living out a different path defined by a unique sequence of quantum branches. This isn't about hopping between realities. These worlds are completely separate and causally disconnected. You will never meet another version of yourself, but the theory insists they are just as real as you are. Critics often point to the theory's violation of Occam's razor, the philosophical principle that the simplest solution is usually the best, proposing an infinite number of unobservable universes to explain how one seems, to some, like the least simple solution imaginable. Yet for its proponents, the elegance is in the math. The many worlds interpretation requires fewer axioms than interpretations that involve a mysterious collapse of the wave function. It treats the entire universe as a single quantum object that evolves deterministically, governed by Schrödinger's equation without exception. The debate continues not about the mathematics, which is sound, but about the philosophical weight we give to this breathtaking vision of reality. It's a theory that asks us to accept that the strangeness of the quantum world isn't confined to tiny particles. It's the engine of existence itself, constantly weaving new worlds into being with every passing moment. The branching worlds of the many worlds interpretation offer one vision of a multiverse, but cosmology presents us with another, perhaps even grander, possibility. This theory suggests that our entire universe might be just one bubble in a vast, frothing cosmic sea, an infinite number of universes, each with its own unique set of physical laws. This is the multiverse born from the theory of eternal inflation, and it provides a stunningly elegant, if controversial, explanation for one of the deepest mysteries of our existence. Why is our universe so perfectly suited for life? To understand this, we need to rewind to the very first moments after the Big Bang. The prevailing cosmological model tells us that the infant universe underwent a period of incredibly rapid expansion known as inflation. This was a sudden, exponential stretching of space-time itself, which smoothed out the cosmos and set the stage for the formation of galaxies. But what if this inflationary period didn't have a clean ending? What if, for most of the cosmos, it never stopped? This is the core of eternal inflation. The idea is that the energy field driving inflation, known as the inflaton field, doesn't decay everywhere at once. Instead, it decays in localized patches like bubbles forming in a pot of boiling water. In each of these pockets, inflation ends, allowing a stable, hot Big Bang universe like our own to form. But outside of these bubbles, the inflaton field remains energized, causing space to continue expanding at a fantastic, exponential rate. This means new bubbles are constantly being formed in the rapidly stretching gaps between the old ones, creating an endless, self-reproducing fractal of universes, a true multiverse. Now, here's where the theory gets truly mind-bending. The laws of physics that govern each of these bubble universes are not necessarily the same. When a bubble forms, the energy of the inflaton field decays into the particles and forces we know, but the way it decays is a random process. This is like a cosmic dice roll that sets the values of nature's fundamental constants. The strength of gravity, the mass of an electron, the power of the nuclear forces. These could all be different in different bubbles. In most of these universes, the dice roll would produce laws that are hostile to any complex structure. A universe where the strong nuclear force is slightly weaker might never form atoms beyond hydrogen. One where the cosmological constant is too large would tear itself apart before the first star could ignite. Our universe, with its seemingly just right constants that allow for galaxies, planets, and life, would be just one particularly fortunate ticket in an infinite cosmic lottery. This leads us directly to the Holographic Principle, a concept that is as debated as it is profound. In its simplest form, it states that we can only observe a universe that is capable of producing us. It's not that the universe was designed for life, but that life inevitably arises in the rare universes where the conditions are accidentally suitable. We shouldn't be surprised to find ourselves in a fine-tuned universe because in all the others, there's no one around to be surprised. For some scientists, this is a powerful explanatory tool. It dissolves the mystery of fine-tuning by placing our universe in a vastly larger context where every possible set of laws eventually exists somewhere. For others, it feels like a cop-out, a philosophical sleight of hand that replaces scientific explanation with a cosmic selection bias. They argue that it effectively makes our universe immune to further explanation, shutting down inquiry by saying, well, it had to be this way for us to be here. The biggest challenge for the inflationary multiverse is testability. If these other universes are forever beyond our causal horizon, separated by regions of space that are expanding faster than light, can we ever gather evidence to support the idea? Proponents suggest there might be ways. If our universe collided with another bubble in the distant past, it could have left an imprint on the cosmic microwave background, a kind of bruise on the sky. Physicists are meticulously searching for such anomalies. Others suggest that the specific details of the particle physics we observe might point towards the type of inflationary model that naturally produces a multiverse. While we may never directly see another universe, we might find fingerprints of the multiverse in the fundamental laws of our own. Whether you see it as the ultimate expression of cosmology or an untestable flight of fancy, the inflationary multiverse forces us to confront the sheer scale of reality and our humble, yet remarkable place within it. But if the multiverse is a cosmic ocean of bubbles, our next theory tries to build a ship to sail it. A single, elegant framework that could describe everything from the dance of quarks to the expansion of the cosmos. This is string theory, and it begins with a simple yet revolutionary shift in perspective. What if the most fundamental building blocks of nature aren't tiny, point-like particles, but unimaginably small, vibrating loops of energy? Think of an infinitely tiny guitar string. Just as a single guitar string can vibrate at different frequencies to produce every possible note, a fundamental string can vibrate in different patterns to manifest as every different kind of particle. One specific resonance gives you an electron, another gives you a quark, another creates the photon that carries light. In this view, the entire universe is a grand, cosmic symphony composed by these vibrating strings. This elegant idea emerges from a desperate need to resolve the single biggest conflict in modern physics, the brutal war between general relativity and quantum mechanics. Einstein's masterpiece, General Relativity, gives us a breathtakingly accurate description of gravity as the curvature of space-time on the largest scales, the dance of planets, and the bending of light around galaxies. Quantum mechanics, on the other hand, is the wildly successful rulebook for the subatomic world, governing the behavior of particles and forces with incredible precision. The problem is, these two rulebooks are written in completely different languages, and they break down when forced to speak to each other. At the center of a black hole, where gravity is immense and the volume is tiny, or at the moment of the Big Bang itself, our math simply explodes into nonsense. We need a theory of quantum gravity to describe these extremes, and string theory is arguably our most promising candidate. By replacing point particles with strings, the theory naturally includes a particle that has the exact properties of the hypothetical graviton, the quantum carrier of the gravitational force. This is a monumental achievement, seamlessly weaving gravity into the quantum tapestry alongside the other forces. But this beautiful unification comes at a cost, and it's a big one: extra dimensions. For the math of string theory to work, these strings can't just vibrate in the 3 spatial dimensions we experience. They require a universe with 10, or in some versions, 11 dimensions. So where are these extra dimensions? The theory suggests they are compactified, or curled up into a space so infinitesimally small that they are completely hidden from our view. A common analogy is a garden hose. From a distance, it looks like a simple one-dimensional line. But if you could shrink down to the size of an ant, you would discover that the hose has a second dimension, a circular one curled around its length. String theory proposes that at every single point in our 3-dimensional space, there are 6 or 7 extra dimensions curled up into a complex, intricate shape called a Calabi-Yau manifold. This leads us to the theory's greatest challenge, the landscape of possible solutions. The specific way these extra dimensions are folded determines the laws of physics within that universe, the strength of forces, the types of particles, even the number of dimensions we perceive. Mathematicians have discovered a staggering number of ways to fold these dimensions, perhaps 10 to the 500 power or more. This is a number so vast it dwarfs the number of atoms in the observable universe. Each folding represents a different possible universe with different physical laws. This means string theory doesn't predict one unique universe, but a nearly infinite multiverse of possibilities. And that makes it incredibly difficult to test. How do you find experimental evidence for one specific configuration when you can't even see the dimensions it describes? This is the central criticism of string theory. After decades of work, it has yet to make a single testable prediction that can be verified in a laboratory. The energy levels required to see a string directly are trillions of times higher than what our most powerful particle colliders can achieve. Some researchers are looking for more indirect signatures, like certain types of supersymmetry or exotic particles that could be leftovers from the early universe. Others hope that precise observations of the cosmic microwave background or gravitational waves might reveal hints of these extra dimensions. But for now, string theory remains a magnificent, untested piece of mathematical architecture. It's a theory of breathtaking beauty and power that promises to unify all of physics, but it remains a promise waiting for the universe to give us the key. It stands as a testament to our deepest desire to find a single, elegant theory of everything, even if that theory ultimately reveals a reality far stranger and more complex than we ever imagined. But if the 10 dimensions of string theory already feel like a mathematical labyrinth, then our next theory adds another layer, quite literally, to the mystery. It's called M-theory, and it emerged in the 1990s as a kind of grand unified theory of string theories themselves. You see, physicists had developed 5 different, self-consistent versions of string theory, each with its own equations and quirks. For a while, this was deeply embarrassing. How could the proposed theory of everything have 5 different competing answers? It was like having 5 different maps for the same city, each claiming to be the only correct one. Then, in 1995, pioneering physicist Edward Witten made a stunning realization. He showed that these 5 string theories weren't rivals at all. They were merely different perspectives, different ways of looking at a single, deeper, and more fundamental reality. That reality is M-theory. The M is intentionally ambiguous. It has been said to stand for membrane, magic, mystery, or even mother, as in the mother of all theories. And at its heart, M-theory introduces a revolutionary new object, the membrane, or brain for short. While strings are one-dimensional loops, brains can exist in multiple dimensions. A 2-dimensional brain is a membrane. A 3-dimensional brain is a solid chunk of something, and the theory allows for brains all the way up to 9 dimensions. In this breathtakingly complex picture, our entire universe could be a 3-dimensional brain floating within a higher dimensional space. The particles and forces we know and love might be stuck to this brain, like waves confined to the surface of the ocean, which is why we can't perceive the full breadth of reality. This new framework also demands an 11th dimension. M-theory is an 11-dimensional theory. This extra dimension provides the mathematical glue that binds the 5 string theories together, showing how they all transform into one another. It's as if we had 5 different 2-dimensional shadows cast by a single 3-dimensional object. M-theory reveals the object itself. And just as in string theory, these extra dimensions are thought to be compactified, curled up into shapes so incredibly tiny that they are far beyond our current ability to detect. This idea of our universe as a brain opens up some truly spectacular possibilities, particularly for explaining the most mysterious force of all, gravity. One of the most puzzling questions in physics is why gravity is so unimaginably weaker than the other fundamental forces. The electromagnetic force between 2 electrons, for example, is about 10 to the power of 40 times stronger than the gravitational force between them. That's a 1 with 40 zeros after it. In M-theory, a compelling solution emerges. What if gravity is weak not because the graviton is fundamentally different, but because it is the only particle that is not confined to our brain? While all other forces are stuck to our 3-dimensional slice of reality, the gravitational force carried by the graviton can leak out into the full 11-dimensional bulk of space. From our perspective on the brain, this dilution of gravity across higher dimensions would make it appear exceptionally feeble. This concept leads to one of the most dramatic potential consequences of M-theory, the idea that the Big Bang itself could have been caused by a collision between our brain and another one in the higher dimensional bulk. This ekpyrotic model suggests that the immense energy released from such a cosmic collision could have created the hot, dense state we identify as the beginning of our universe without the need for a singularity. It's a cyclical vision of creation where universes are born and reborn through collisions in a hidden, higher dimensional space. The primary challenge with M-theory, however, remains its sheer mathematical complexity and the daunting lack of experimental evidence. The energy scales required to probe these extra dimensions or to vibrate a string directly are far beyond the reach of any particle accelerator we could ever hope to build. Furthermore, M-theory doesn't make a single, unique prediction about our universe. Instead, it describes a vast landscape of perhaps 10 to the 500 possible solutions, each corresponding to a universe with different physical constants and laws. Our universe, with its specific rules, would be just one point in this colossal landscape. For some, this is a profound insight into the nature of reality. For others, it's a major weakness as it makes the theory incredibly difficult to falsify. Despite this, M-theory remains one of the most ambitious and mathematically sophisticated attempts to achieve the holy grail of physics. A single, complete theory of everything that seamlessly unites the quantum world with the cosmos. But while M-theory weaves gravity into a tapestry of extra dimensions, another powerful idea takes a completely opposite approach. Instead of adding new layers to reality, it seeks to rewrite the rules of gravity right here in our own four-dimensional space-time by breaking it down into its most fundamental building blocks. This is loop quantum gravity, or LQG, and it is string theory's most formidable rival in the quest for a theory of quantum gravity. Where string theory is built on the idea of tiny, vibrating strings, loop quantum gravity proposes something even more radical. That space itself is not smooth and continuous as Einstein described, but is instead woven from a fabric of finite, discrete loops. Think of the fabric of the cosmos not as a perfectly smooth sheet, but as an incredibly fine mesh, a network of interconnected threads where each tiny loop is a single atom of space. This profound idea emerges from a deep respect for Einstein's general relativity. The goal of LQG isn't to unify all forces, but to successfully apply the principles of quantum mechanics specifically to gravity by quantizing the geometry of space-time itself. In this theory, the familiar three-dimensional space we move through is actually built from a web of these elementary loops called a spin network. These networks define the volume and area of any region of space with a precise, granular precision. There is a smallest possible volume, a smallest possible area, a true pixelation of reality. This means you cannot divide space infinitely. There is a fundamental limit, a quantum of space, just as there is a quantum of light in a photon. This solves a major problem that plagues other theories, the dreaded singularity. In the standard models of physics, both the center of a black hole and the beginning of the Big Bang are points of infinite density and zero volume, where the laws of physics break down completely. But in loop quantum gravity, you cannot have a zero volume. The theory predicts that instead of a Big Bang singularity, there was a big bounce. A previous contracting universe could have reached a point of maximum density, and then quantum gravitational effects caused it to rebound, expanding outward into our own universe. The Big Bang wasn't a beginning from nothing, but a transition from a prior cosmic phase. The theory also makes a stunning prediction about black holes. It provides a way to calculate the entropy of a black hole, the number of quantum microstates that correspond to its macroscopic appearance, and the result matches exactly what Jacob Bekenstein and Stephen Hawking predicted decades earlier. This is a major victory, suggesting that the theory is on the right track by describing black holes as objects with a discrete, quantized geometry. Of course, such a revolutionary idea begs for experimental proof. How do we test for the granular structure of space? One promising avenue is to look for its effect on the speed of light. Due to this pixelated structure, very high-energy photons, like those found in gamma-ray bursts from the distant universe, might travel at very slightly different speeds. A low-energy photon and a Chinese letter 1 might be like two cars driving on a cobblestone road versus a smooth highway. The ride is subtly different. If we could detect this energy-dependent speed of light across billions of light-years, it would be a powerful hint that we are seeing the quantum grain of space-time itself. Another potential test involves looking for a subtle blurring in the images of extremely distant astrophysical objects. While the search for this evidence is ongoing and incredibly challenging, it represents a tangible path forward for validating one of the most profound ideas about the hidden architecture of our universe. Loop quantum gravity offers a starkly different, yet equally compelling, vision from string theory, one where the hidden force isn't in extra dimensions, but in the very quantum threads from which space and time are spun. Now we arrive at a theory that turns our understanding of gravity completely on its head. After centuries of viewing it as a fundamental force woven into the fabric of space-time, what if gravity is something else entirely? What if it's not a primary ingredient of the universe, but a secondary effect, a kind of cosmic mirage? This radical proposal is known as emergent gravity, and it comes from the mind of theoretical physicist Eric Verland. His idea is as profound as it is simple. Gravity doesn't exist on the most fundamental level. Instead, it emerges from something much more primitive, information. To grasp this, it helps to think about a concept we all understand: temperature. If you hold your hand near a fire, you feel heat. But what is heat really? At its core, temperature isn't a fundamental property. It emerges from the collective, chaotic motion of trillions of molecules. You can't assign a temperature to a single molecule. It's a statistical property that only has meaning for a vast crowd. Verland proposes that gravity is exactly the same. We feel its pull and see its effects, but it's not a force in its own right. It's a side effect, an emergent phenomenon that arises from the behavior of something even more basic: the bits of information that make up the universe. This idea finds its roots in some of the most puzzling discoveries about black holes. As we touched on earlier, a black hole's entropy, its information content, is proportional to the area of its event horizon, not its volume. This was a huge clue that the deepest workings of reality might be two-dimensional, holographic. Verland took this holographic principle and ran with it. He proposed that space itself can be thought of as being built from a vast network of interconnected information. The position of matter isn't defined by coordinates in a void, but by how it affects the information stored on a distant holographic boundary. When you place an object in this space, it effectively changes the amount of information or entropy on that boundary, and this is where the illusion of gravity comes in. Verland's math shows that this tendency for entropy to increase, a fundamental law of thermodynamics, naturally gives rise to a force that behaves exactly like gravity. An apple falls from a tree not because it's being pulled by a fundamental force, but because it's being guided by the universe's innate tendency to move towards a state of higher disorder. The mass of an object, in this view, isn't an intrinsic property. It's a measure of how much that object disrupts the information content of space. This is a complete inversion of Einstein's view, where mass tells space how to curve. Here, information tells mass how to behave. The most stunning implication of this is for the dark universe. If gravity is emergent, then the need for dark matter particles simply vanishes. The observed gravitational effects we attribute to dark matter, the way galaxies rotate too fast, the way light bends around them, could just be a result of this emergent gravitational behavior on large scales. The extra pull isn't coming from invisible matter. It's coming from the way the information structure of the universe responds to visible matter. In some calculations, Verland's equations reproduce galaxy rotation curves with remarkable accuracy, matching observations without a single exotic particle. The theory also offers a new perspective on dark energy, suggesting it could be linked to the universe's total information capacity as it expands. Naturally, such a paradigm-shifting idea is met with intense scrutiny and controversy. The physics community is deeply divided. Proponents hail it as a breathtakingly elegant solution that does away with the decades-long hunt for particles we've never seen. Critics point out significant challenges. The theory, in its current form, struggles to explain phenomena like the precise observations of the bullet cluster, where gravitational lensing clearly shows a separation between the visible matter and the source of gravity. It also hasn't yet been successfully integrated with the quantum world in a complete way. The quest now is to find a way to test it. Researchers are looking for any subtle deviation from the predictions of Newton and Einstein that emergent gravity might produce, perhaps in the ultra-weak gravitational fields at the edges of galaxies or in laboratory experiments designed to probe the nature of gravity itself. Verland's theory remains a powerful, provocative thought experiment that forces us to question our most basic assumptions. It suggests that the force that holds our feet to the ground and our planet in orbit might be the universe's most convincing illusion, a ghostly afterthought born from the deep informational code of reality. If the idea of emergent gravity challenges our understanding of force, then our next theory exposes a numerical rift so vast it has been called the worst prediction in the history of physics. This is the cosmological constant problem, and it represents a stunning disconnect between our two most successful theories, quantum mechanics and general relativity, creating a puzzle that lies at the very heart of our existence. To understand it, we have to start with a seemingly simple concept: nothing, empty space, a perfect vacuum. We used to think of a vacuum as truly empty, a void completely devoid of anything. But quantum field theory tells a very different story. According to the rules of the quantum world, empty space is not empty at all. It's a seething, bubbling foam of virtual particles. Particle-antiparticle pairs constantly flicker into and out of existence, borrowing energy from the vacuum for an impossibly brief moment before annihilating each other. This isn't just theoretical. We see the effects of this quantum jitter in measurable phenomena like the Casimir effect. All of this frantic activity should contribute an enormous amount of energy to the vacuum itself. This is the vacuum energy, and when we use our quantum theories to calculate just how much energy there should be, we get a number that is almost beyond comprehension. The math predicts a vacuum energy density of around 10 to the power of 112 ergs per cubic centimeter. This is the theoretical expectation. Now let's switch to the view from cosmology. In his theory of general relativity, Einstein introduced a term called the cosmological constant, represented by the Greek letter lambda. He originally added it to keep the universe static, later calling it his greatest blunder when the universe was found to be expanding. But the concept was revived with the discovery of dark energy. We now observe that the expansion of the universe is accelerating, and the simplest explanation for this is a very small, positive cosmological constant, a form of energy inherent to space itself. When astronomers measure the actual value of this energy, based on the observed rate of the universe's expansion, they get a result that is about 10 to the power of -8 ergs per cubic centimeter. Let's put those two numbers side by side. The prediction from quantum theory is 10 to the power of 112. The observed value from cosmology is 10 to the power of -8. That's a discrepancy of 120 orders of magnitude. To say the predicted value is larger is a catastrophic understatement. The predicted vacuum energy is greater than the observed value by a factor of 1 followed by 120 zeros. If our quantum calculation were correct, the energy contained in every cubic centimeter of so-called empty space would be so immense that the universe would have ripped itself to shreds immediately after the Big Bang. Galaxies, stars, planets, and life could never have formed. The fact that we are here to measure it means something is profoundly wrong with our understanding. This colossal failure of prediction suggests a deep flaw in our physics. Quantum field theory and general relativity are both brilliantly successful in their own domains, but when we try to combine them to understand the energy of nothingness, they produce this nonsensical result. It's as if two master chefs followed their own perfect recipes, but when they combined their ingredients, they created a toxic, inedible sludge instead of a gourmet meal. This isn't just a small error to be corrected. It's a screaming signal that we are missing a fundamental piece of the puzzle. So what are the potential solutions? One of the most promising ideas we've already discussed is supersymmetry. In a perfectly supersymmetric universe, the contributions of particles and their superpartners to the vacuum energy would be exactly opposite and would cancel each other out, potentially bringing the net value down to zero. The problem is, we don't live in a perfectly supersymmetric universe. We see no evidence of these partner particles at the energy scales we can access, so the cancellation must be imperfect, leaving a tiny remnant. While this could explain a small value, it doesn't explain why that value is the specific, incredibly tiny number we observe. This leads us to a more philosophical, and some would say controversial, explanation, the anthropic principle. In the context of the inflationary multiverse, if there are a vast number of universes, each with a randomly different value for the cosmological constant, then we obviously must find ourselves in one where the value is small enough to allow for the formation of galaxies and life. In most universes, the constant is too large and the universe expands too fast for anything to form, or it's negative and the universe collapses immediately. Only in a rare, privileged subset can observers like us arise. This isn't so much a solution as a change in perspective. It explains why we observe such a fine-tuned number without explaining the physics behind the tuning itself. For some, this is a profound insight into the nature of reality. For others, it's an unsatisfying retreat from a fundamental scientific explanation. Other proposals are even more radical. Some physicists suggest that the constants of nature, including the cosmological constant, might not be true constants at all. They could be dynamic fields that evolve to their current values over time or that vary across space. Another idea is that there is a mysterious yet unknown symmetry principle that forces the cosmological constant to be zero, and that dark energy is something else entirely, perhaps a dynamical field called quintessence. The cosmological constant problem remains a wide-open frontier, a silent monument to the limits of our current knowledge and a powerful reminder that the deepest secrets of the cosmos are often hidden in plain sight, in the overwhelming energy of nothingness that fills every corner of our reality. While the cosmological constant frames dark energy as a fixed, unchanging feature of empty space, another compelling theory brings it to life. This is the concept of quintessence, a dynamic and evolving form of dark energy that could not only explain the present acceleration of the universe but also predict a dramatically different cosmic future. The name itself is a nod to history. In ancient Greek philosophy, the quintessence was the elusive fifth element beyond earth, air, fire, and water that filled the heavens and composed the stars. In modern cosmology, it represents a fifth fundamental force, a cosmic fluid whose properties change over the lifetime of the universe. Unlike the stubborn, constant energy of a cosmological constant, quintessence is imagined as a scalar field that permeates all of space. Think of a scalar field like a weather map that shows only one piece of information at every point, like temperature or air pressure. The quintessence field has a value at every point in space, and that value isn't fixed. It can roll, shift, and evolve over billions of years, much like a ball rolling down a complex, tilted landscape. The way this field evolves determines the strength and behavior of the dark energy it produces. In its simplest form, the field started with a high potential energy in the early universe, which caused it to roll slowly, acting almost like a cosmological constant and driving the period of inflation. As it rolled further down its potential slope, its energy density decreased, allowing matter to dominate and galaxies to form. But then, as the universe expanded and grew more diffuse, the field's dynamics changed again. It may have reached a shallower, flatter part of its slope, causing its roll to slow to a crawl. In this regime, its pressure becomes strongly negative, and it begins to act like a repulsive force, overcoming gravity and driving the accelerated expansion we see today. This dynamic nature is the theory's greatest strength. It offers an elegant explanation for why the acceleration of the universe began when it did around 5 billion years ago, rather than immediately after the Big Bang. A cosmological constant is always on, so why did it take over so recently? Quintessence provides a natural answer. The field's energy density only became dominant over matter density as the universe expanded and matter was diluted. It also opens up a spectrum of possible futures for our cosmos that are far more varied and dramatic than the lonely, cold fate of a lambda CDM universe. Depending on the exact shape of the field's potential, the future could hold several paths. The acceleration could continue forever, leading to a big freeze where galaxies vanish over the horizon. The field could eventually decay, turning its energy into particles and allowing the universe to return to a matter-dominated state. Or, in a truly apocalyptic scenario called the Big Rip, the repulsive force of quintessence could grow infinitely strong over time, eventually overcoming all other forces. In this finale, first galaxies would be torn apart, then solar systems, then planets, and finally, the very atoms that make up all matter would be ripped to shreds at a precise moment in the future. The connections to other profound theories are also tantalizing. The inflationary field that blew up the early universe was also a scalar field, leading many physicists to wonder if quintessence is somehow its late-time cousin, a second act for the engine of creation. Furthermore, string theory's landscape of 10 to the 500 possible vacuum states provides a natural home for quintessence, as many of those states could correspond to universes with rolling scalar fields of their own. The challenge, as with so many of these beautiful ideas, is evidence. How do we distinguish a rolling quintessence field from a simple, static cosmological constant? Astronomers are searching for a telltale signature, a change in the equation of state of dark energy. If the W value, which characterizes the pressure-to-density ratio of dark energy, is exactly -1, it points to a cosmological constant. But if observations can show that W is evolving, becoming more or less negative over cosmic time, it would be a powerful vote for a dynamic model like quintessence. Missions like the Roman Space Telescope and the Vera C. Rubin Observatory are designed to make these ultra-precise measurements, charting the expansion history of the universe with unprecedented detail to see if dark energy is truly constant or if it has a life of its own. While quintessence imagines a dynamic field that evolves over cosmic time, another theory proposes a field that is actively hiding from us, changing its very nature to escape detection. This is the concept of chameleon fields, a hypothetical type of scalar field whose properties are not fixed, but instead shift to blend in with their local environment, much like their namesake reptile. The theory, developed by physicists Justin Cowrie and Amanda Weltman, offers a cunning solution to one of the biggest puzzles surrounding dark energy and modified gravity. If such a fifth force is so powerful on cosmic scales, why can't we find any evidence of it here on Earth or in our solar system? The chameleon's answer is brilliantly simple because it's hiding in plain sight. The core idea is that the mass of the chameleon particle, the quantum of this field, is not a constant. It depends dramatically on the density of its surroundings. In the deep vacuum of interstellar space, where the matter density is incredibly low, the chameleon field would be very light and have a long range, allowing it to act as a smooth, repulsive force that drives the accelerated expansion of the universe. This would make it a perfect candidate for dark energy, but bring this field into a high-density environment like a planet, a laboratory, or even our atmosphere, and its behavior changes completely. The field's mass becomes very large and its range shrinks to a microscopic distance. It effectively shuts itself off, becoming so short-ranged that it is virtually undetectable with conventional equipment. This is why our most sensitive experiments on Earth have failed to find any sign of a fifth force. The chameleon is an expert at camouflage. This elusive nature makes detecting a chameleon field an extraordinary challenge, requiring incredibly clever and precise experiments. One of the most promising techniques is atom interferometry. This involves using ultra-cold atoms, chilled to a fraction of a degree above absolute zero, and dropping them in a vacuum chamber to create a matter wave interferometer, essentially using the quantum wave nature of atoms as an exquisitely sensitive probe for tiny forces. Researchers look for any anomalous acceleration or extra pull between a dense source mass and a cloud of these atoms that could signal the presence of a chameleon particle trying to hide. Other experiments involve using neutrons bouncing between mirrors or searching for energy loss in afterglow photons from strong magnetic fields. The goal is to create a low-density vacuum cavity right here on Earth and then bring a massive object close to it, trying to tempt the chameleon field to reveal itself in the gap between the vacuum and the matter. Beyond explaining dark energy, chameleon fields present a fascinating bridge between particle physics and cosmology. They are a form of modified gravity, but one that is specifically designed to evade the tight constraints set by decades of precise solar system tests of Einstein's general relativity. By being effectively invisible in our high-density neighborhood, the chameleon avoids contradicting the well-established observations of planetary orbits and the bending of starlight. The theory's implications are profound, suggesting that the laws of physics we measure in our labs might not be the full story. They could be a local set of rules specific to our dense environment, while the universe at large operates under a slightly different, more expansive set of principles that only reveal themselves in the deepest voids of space. Whether these elusive fields are a real part of nature's palette or just another beautiful mathematical phantom remains one of the most intriguing hunts in modern physics. Yet for all its success, the Standard Model still holds a few deep, unanswered questions, and one of the most stubborn is known as the strong CP problem. It's a subtle issue involving the nuclear strong force, and it asks why certain interactions between quarks and gluons, which the math allows for and even seems to predict, are never observed in nature. The equations suggest the universe should exhibit a specific kind of asymmetry, but our observations show it is perfectly symmetric. It's as if a fundamental law of physics has a glaring exception that no one can explain. This is where the action enters the picture. In 1977, physicists Roberto Pexi and Helen Quinn proposed an elegant solution. They suggested a new symmetry in nature that would naturally cancel out this problematic CP violation, making the observed symmetry a fundamental feature of reality. Shortly after, Frank Wilczek and Steven Weinberg realized that this new symmetry would inevitably predict the existence of a new, very light neutral particle. Wilczek named it the Action after a brand of laundry detergent because it was a particle that cleaned up a problem in physics. What started as a clever fix for a quantum puzzle has blossomed into one of the most compelling candidates for the mysterious substance we call dark matter. Actions are theorized to be incredibly light, potentially billions of times lighter than an electron, and they would interact with ordinary matter only very weakly through gravity and perhaps a slight electromagnetic coupling. They would be produced in vast numbers in the hot, dense early universe, essentially freezing out as a coherent, cold background field that permeates all of space. Their properties are exactly what cosmology requires for a cold dark matter particle. They are cold, meaning they moved slowly in the early universe, allowing them to clump together and form the gravitational scaffolding for galaxies. They are stable, not decaying over cosmological timescales, and they are abundant enough to account for the missing mass we observe. Their unique nature allows for an even more fascinating possibility, because they are bosons, particles that can occupy the same quantum state, and because they are so cold and numerous, they could collectively condense into a state known as a Bose-Einstein condensate. This isn't a cloud of individual particles, but a single, coherent quantum object that behaves like a wave on an astronomical scale. An entire galaxy could be immersed in this ghostly condensate, a single wave function stretching across light years. This would explain why actions don't just form a diffuse cloud around galaxies. They can cluster and behave exactly like the cold dark matter halos we infer from galactic rotation curves. This possibility has spurred a global hunt for these elusive particles, using some of the most ingenious experiments ever devised. The most prominent is the Action Dark Matter experiment, or a ADMX. Its principle is beautifully clever. If actions exist as a condensate permeating our galaxy, they should be streaming through this room and through you right now. And due to their slight electromagnetic coupling, a very strong magnetic field could, in theory, cause them to convert into microwave photons. A DMX is essentially a powerful, tunable radio receiver inside a massive superconducting magnet. It's designed to listen for a faint, specific frequency microwave whisper that would be the signature of an action converting into a photon. The experiment must be cooled to near absolute zero to eliminate thermal noise and is exquisitely tuned to scan through millions of possible frequencies, one at a time, hoping to catch the faint signal of an action with a specific mass. This approach highlights a key advantage actions have over their main dark matter rival, the WIMP, or weakly interacting massive particle. While WIMP detectors must be placed deep underground to shield them from cosmic rays and other background radiation, action hunters like a DMX are largely immune to such interference. The signal they are looking for is a single, precise frequency that stands out clearly from the background noise. It's a painstakingly slow process, a meticulous search through a vast desert of possible masses, but a single, verifiable signal would be an earth-shattering discovery, simultaneously solving one of particle physics' deepest puzzles and revealing the identity of the invisible matter that shapes the cosmos. The quest for the action is a perfect blend of theoretical elegance and experimental brilliance, a search for a particle born from a problem of symmetry that may hold the key to the universe's hidden architecture. But what if our cosmic inventory isn't just missing one thing, but we've been categorizing it incorrectly from the start? For decades, the leading candidate for dark matter has been cold dark matter, slow-moving, heavy particles that clump together easily to form the large-scale structures we see. This model, known as lambda CDM, has been incredibly successful at explaining the universe on the grandest scales, the cosmic web of filaments and voids. Yet, when we zoom in to look at the finer details within and around individual galaxies, some persistent puzzles emerge. This is where a fascinating alternative steps into the spotlight, the theory of warm dark matter. The key difference is right in the name, temperature. But in cosmology, temperature doesn't refer to heat in the way we normally think of it. It refers to a particle's velocity or how fast it was moving in the early universe. Cold dark matter particles, like the theorized WIMP, would have been moving very slowly, allowing them to collapse into small, dense clumps immediately. Warm dark matter particles, on the other hand, would have been born with a significant amount of thermal energy, zipping around at much higher speeds. This might sound like a minor detail, but it has profound consequences for how galaxies are built. The most prominent candidate for a warm dark matter particle is the sterile neutrino, a hypothetical, heavier, and more elusive cousin to the standard neutrinos we know, one that interacts only through gravity. This higher thermal velocity acts like a cosmic smoothing iron, while cold dark matter can collapse into a vast number of very small, dense clumps. Warm dark matter particles, with their faster motions, would have washed out these tiny fluctuations in the primordial universe. They simply couldn't settle down into the smallest gravitational wells. This means a universe with warm dark matter would have far fewer of the smallest dwarf galaxies orbiting larger ones like our Milky Way. And this is precisely why many cosmologists find the idea so appealing. It offers a potential solution to the infamous missing satellites problem. Our most sophisticated supercomputer simulations of galaxy formation, based on the cold dark matter model, predict that a galaxy the size of the Milky Way should be surrounded by thousands of small satellite dwarf galaxies. Yet when we look, we only observe a few dozen. Where are all the others? Warm dark matter provides an elegant answer. They were never there to begin with. The particle's innate thermal energy prevented the formation of such minuscule dark matter halos in the first place, naturally resulting in a satellite population much closer to what we actually observe. It also helps address other small-scale issues, such as the fact that the dense centers of simulated dark matter halos appear to be too cuspy, and concentrated compared to the gentler cores we infer from the rotation of real galaxies. However, every potential solution brings its own set of challenges, and warm dark matter is no exception. The strongest constraints on this theory come from an unexpected cosmic tool, the Lyman alpha forest. This isn't a literal forest, but the beautiful, complex pattern of absorption lines seen in the light from the most distant quasars. As this ancient light travels through the cosmos, it passes through clouds of neutral hydrogen gas that imprint a distinctive forest of lines on the spectrum. This pattern is incredibly sensitive to the distribution of matter in the universe. By analyzing it, astronomers can effectively map the cosmic web and measure how much small-scale structure existed at very early times. These observations have placed tight limits on just how warm dark matter can be. If the particles were too fast-moving, they would have smoothed out too much of the small-scale structure, erasing features in the Lyman alpha forest that we clearly see. The data suggests that if warm dark matter does exist, it must be a Goldilocks scenario, not so cold that it creates too many tiny satellites, and not so warm that it prevents the formation of the smaller structures we know are present. The search for sterile neutrinos and other warm dark matter candidates is a major frontier in both particle physics and astronomy. Experiments are underway to try and detect the faint X-ray signal that would be produced if a sterile neutrino decayed. Others are using powerful telescopes to conduct ever more detailed censuses of the smallest, faintest dwarf galaxies in our local cosmic neighborhood, looking for a number that will either bolster or challenge the warm dark matter hypothesis. This ongoing investigation reminds us that the hidden forces shaping our universe might not be a single, monolithic entity, but a spectrum of possibilities, each leaving a unique fingerprint on the cosmos we are only just learning to read. But what if the answer to the dark matter puzzle isn't a new, exotic particle at all, but something we already know exists just from a different era of creation? This brings us to a theory that is as elegant as it is ancient, the idea that dark matter is made of primordial black holes. Unlike the stellar black holes formed from the collapse of massive stars, these would be relics from the universe's explosive first second, and they could be hiding in plain sight throughout the cosmos. The concept is breathtakingly simple. In the incredibly hot, dense conditions just after the Big Bang, random quantum fluctuations in density could have been amplified by the rapid inflation of space-time. In some regions, the density might have become so extreme that gravity caused the space itself to collapse, directly forming black holes. This process wouldn't require stars or supernova. It would be a direct birth from the energy of the newborn universe. Because of this unique origin, these primordial black holes could have formed in a vast range of sizes, from microscopic ones smaller than an atom that may have already evaporated due to Hawking radiation, to ones with the mass of an asteroid, a planet, or even a star. It is this diversity that makes them such compelling candidates. A vast population of asteroid mass or planet mass black holes scattered throughout the halos of galaxies would be completely dark, would interact only through gravity, and could easily account for the missing mass that holds galaxies together. For a long time, this theory was largely sidelined. The main objection was that if there were enough of these objects to explain all of dark matter, we should have seen their effects through a phenomenon called gravitational microlensing. The idea is that if a primordial black hole were to pass directly between Earth and a distant star, its gravity would act as a lens, bending the starlight and causing the star to temporarily brighten. Extensive surveys like the Macho and Eros projects scanned millions of stars in nearby galaxies for years, looking for these telltale flashes. While they found a few candidate events, the number was far too low to account for all the dark matter, seemingly ruling out a universe filled with black holes in the mass range of a large planet to about 10 times the mass of our Sun. Just when the case seemed closed, a monumental discovery from a completely different field of astronomy breathed startling new life into the idea. In 2015, the LIGO observatory made history by directly detecting gravitational waves for the first time. The signal came from the merger of two black holes, each about 30 times the mass of our Sun. This was surprising in itself, as stellar evolution models struggled to explain how such heavy black holes could form through conventional means. But the real shock came from the analysis of their spins. The data suggested these black holes were not aligned with each other, which is something you would expect if they had been born together in a binary star system. Instead, it seemed more likely they had formed independently and found each other later in life within a dense cluster of objects. This immediately led scientists to ask, what if these weren't stellar black holes at all? What if they were primordial black holes formed in the early universe and drifting like ghosts through a dark matter halo? The fact that LIGO has since detected several more of these heavy mergers has kept this tantalizing possibility wide open. The search is now on to find these elusive objects across all possible mass ranges. For the smaller asteroid mass black holes, new experiments are proposed that could detect the faint ripples in space-time they would produce as they zip through our solar system, or the unique flash of light if one were to evaporate in a final burst of energy. In the intermediate mass range, where microlensing surveys placed their strongest constraints, astronomers are using powerful new telescopes to monitor hundreds of millions of stars with unprecedented sensitivity, hoping to catch the rare and subtle lensing event caused by a lone, drifting black hole. The beauty of this theory lies in its minimalist approach. It doesn't require inventing a new particle or a new force. It only requires that the violent birth of the universe created gravitational traps that have been weaving through the cosmos unseen for over 13 billion years. Whether they are the sole answer to dark matter or just one component of a more complex cosmic recipe, primordial black holes represent a profound connection between the universe's first instant and the hidden architecture we live within today. These ideas of actions, warm dark matter, and primordial black holes showcase our incredible ingenuity in chasing the invisible, but they all operate within a familiar framework. They are searching for a thing, a particle or an object to explain the missing mass. Our next theory takes a completely different approach, questioning not what dark matter is, but the very nature of one of our most celebrated discoveries. We're venturing into the world of Technicolor and the composite Higgs, a radical reimagining of where mass itself comes from. To appreciate this, we first have to revisit the crowning achievement of the Standard Model, the Higgs mechanism and the discovery of the Higgs boson. In this view, mass isn't an innate property. Particles are massless until they wade through the cosmic molasses of the Higgs field, which exists everywhere in space. Their interaction with this field is what gives them inertia, what makes them heavy. The Higgs boson is the visible ripple in that field. It's an elegant idea, and its confirmation at the Large Hadron Collider was a monumental triumph. But for some physicists, it feels a bit like a cheat. Why should this one fundamental, seemingly arbitrary field be responsible for such a fundamental property? Technicolor theories offer a more dynamic mechanical answer. Mass doesn't come from a field you swim through, but from a force that holds you together. The name Technicolor is a brilliant play on words, drawing a direct analogy to the strongest force we already know, the strong nuclear force described by quantum chromodynamics, or QCD. In QCD, quarks are bound together by the exchange of gluons to form composite particles like protons and neutrons. Crucially, these composite particles are heavy, far heavier than the sum of the tiny masses of the quarks inside them. Where does that extra mass come from? It comes from the immense binding energy of the strong force itself, thanks to Einstein's E equals mc squared. Energy and mass are two sides of the same coin. Technicolor proposes that a new, similar force exists, a techni-strong force. This force would act on a new set of fundamental particles called technoquarks, binding them together into composite particles. Some of these composites would be the W and Z bosons that carry the weak nuclear force, and crucially, another would be what we call the Higgs boson. In this view, the Higgs isn't fundamental at all. It's a composite particle, a techni-meson, and its properties, including its role in giving other particles mass, emerge from this new strong dynamics, just like a proton's mass emerges from QCD. This is a breathtakingly economical idea. It doesn't just explain the origin of mass, it unifies the explanation with the mechanism that generates the masses of the W and Z bosons, all through the dynamics of a single new force. It paints a picture of a universe where the laws of physics are more uniform, relying on a proven mechanism, strong force dynamics, rather than invoking a unique and solitary Higgs field. So why isn't this the accepted model? The discovery of the Higgs boson in 2012 was both a victory and a challenge for Technicolor. The particle that was found had a mass of about 125 billion electron volts, which is remarkably light for a composite object. If the Higgs were composite, built from technoquarks bound by a new strong force, we would expect to see a whole host of other composite particles, similar to the pion and rho mesons we see in QCD. These heavier techni-mesons and techni-baryons should have shown up at the LHC, but so far they haven't. Furthermore, the properties of the detected Higgs boson, specifically how it couples to other particles, match the predictions of the standard fundamental Higgs model with stunning precision. There's no clear signature of the compositeness that Technicolor predicts. Yet, the door is far from closed. The simplest, most minimal versions of Technicolor may be ruled out, but more sophisticated composite Higgs models are very much alive. These models tweak the idea, often incorporating elements of supersymmetry or existing in higher dimensions, to explain why the Higgs looks so fundamental even if it isn't. They predict that the new force becomes strong at a much higher energy scale, making the composite structure of the Higgs too small for the LHC to directly probe. The telltale signs of compositeness might be incredibly subtle deviations from the standard model predictions, tiny anomalies in the rates of rare particle decays or precise measurements of the Higgs boson's interactions. Finding these deviations is a primary goal of the high luminosity upgrade to the LHC and of proposed future colliders. The hunt is on not for dramatic new particles, but for the faintest of fingerprints left by a hidden force that might be building reality from the ground up. If the idea of our universe as a brain made you question the very stage upon which reality plays out, then our next theory invites you to consider that the stage itself might be far grander and more twisted than we ever perceived. We're moving beyond the tiny, curled-up dimensions of string theory to explore the possibility that extra dimensions could be large or even warped, hiding in plain sight and reshaping our understanding of gravity itself. For centuries, we've accepted that our physical reality consists of three spatial dimensions: length, width, and height, plus time. It's an intuitive picture, but it might be a profoundly local one. The revolutionary idea here is that there could be additional spatial dimensions that are not microscopically small, but could be vast, perhaps even infinite in size. The reason we don't see them, the theory suggests, is because the particles that make up our bodies and our world are stuck, confined to a three-dimensional membrane or brain within this higher dimensional space. Imagine a line drawn on a piece of paper. An ant living on that line would only be aware of forward and backward. It would be completely oblivious to the vast second dimension of the paper's surface stretching away to either side. In the same way, we three-dimensional beings might be trapped on our own brain, unaware of the full expanse of the cosmos. This concept provides a stunningly elegant explanation for the most perplexing hierarchy problem in physics. Why is gravity so incomparably weaker than the other fundamental forces? The electromagnetic force is 10 to the power of 40 times stronger. That's a 1 with 40 zeros after it. If gravity is so fundamental, why is it such a feeble whisper in comparison? The answer might be that while the other forces are confined to our brain, gravity, embodied by the graviton, is not. It can leak out or propagate into the full volume of the higher dimensional space. From our perspective, this dilution of the gravitational force across extra dimensions makes it appear incredibly weak. It's not that gravity is inherently weak, it's that most of its strength is bleeding into dimensions we cannot access. This idea was spectacularly refined in the late 1990s by physicists Lisa Randall and Raman Sundram. They proposed a brilliant model involving a warped fifth dimension. Picture two three-dimensional brains floating in a five-dimensional bulk. One brain is ours, the visible brain, where we live with all the particles of the standard model. The other is a hidden brain. The space between them isn't flat, it's intensely warped, curved by a huge amount of energy. This warping, often compared to the curvature of space-time near a black hole, creates an exponential scale factor. In their model, the fundamental scale of gravity in the full five-dimensional space could actually be as low as the electroweak scale, solving the hierarchy problem naturally. All the incredible weakness of gravity we experience is just a result of this warping. It's diluted across this curved dimension. The Higgs field, and therefore all mass, is localized on our brain, but gravity is free to feel the full geometry of the higher dimensional reality. Of course, a theory this radical demands experimental proof. How could we possibly detect these large extra dimensions? Scientists are pursuing several ingenious methods. The first looks for deviations in the force of gravity itself at incredibly small distances. If there are large extra dimensions, gravity should stop obeying the familiar inverse square law at scales comparable to the size of those dimensions. Experiments using exquisitely sensitive torsion balances are measuring the gravitational attraction between objects separated by mere micrometers, searching for any telltale sign that gravity is suddenly becoming stronger at tiny ranges as we probe into the higher dimensional regime. The second method uses the world's most powerful particle colliders. If the fundamental scale of gravity is indeed lowered into the multi-teraelectronvolt range, as some models suggest, then the Large Hadron Collider could literally create microscopic black holes. These wouldn't be the terrifying gravitational monsters of mythology. They would be ephemeral quantum objects that would instantly evaporate in a shower of particles via Hawking radiation. Detecting such an event would be the smoking gun for extra dimensions. Alternatively, colliders could look for missing energy, a signature that a graviton has been produced and then carried energy away into the higher dimensional bulk, vanishing from our detectors entirely. The implications of large extra dimensions are nothing short of cosmic. They suggest that the true home of reality is a higher dimensional space, and our familiar four-dimensional world is just a slice, a surface. It recontextualizes our entire existence, suggesting that the deepest laws of the universe are playing out on a stage we are only beginning to imagine. The search for these dimensions is a direct probe into the hidden architecture of everything, a quest to see if the universe's greatest secrets are written not just in the particles we know, but in the very geometry of the dimensions we have yet to see. But this exploration of hidden dimensions and gravitational leaks brings us to a profound quantum phenomenon that challenges the very notion of what is real and what is simply a matter of perspective. This is the Unruh effect, named after physicist William Unruh, and it proposes that the particles you perceive in the universe depend entirely on your state of motion. Imagine you are floating in the deepest, darkest, most perfect vacuum of space. According to all the standard rules of quantum field theory, you would detect absolutely nothing, a complete and utter void. But now, imagine you fire up a rocket pack and begin to accelerate faster and faster. According to the Unruh effect, you would no longer be surrounded by nothingness. Instead, your ultra-sensitive instruments would begin to detect a warm bath of particles popping into existence all around you. To you, the accelerating observer, the vacuum is now full of heat and light. Yet, to a friend floating inertially nearby, the space around you remains completely and utterly empty. Both of your measurements are correct, and this reveals a deep, unsettling truth. Particles are not fundamental entities. What one observer sees as a bustling crowd of real particles, another sees as nothing more than the ghostly fluctuations of empty space. This bizarre effect is deeply connected to one of the most famous predictions in all of physics, Hawking radiation. Stephen Hawking calculated that black holes aren't completely black. They should slowly evaporate by emitting a faint glow of thermal radiation from their event horizons. The math behind Hawking's discovery and the Unruh effect is remarkably similar. In both cases, it's the presence of a horizon that creates the particles. For someone accelerating uniformly, there is a point behind them, a Rindler horizon, that they can never receive signals from, just as an astronaut falling into a black hole can never send signals out past the event horizon. This horizon disrupts the quantum vacuum, and that disruption manifests as a thermal bath of particles whose temperature is directly proportional to the acceleration. The faster you accelerate, the hotter this phantom glow becomes. For the acceleration to produce a temperature even remotely detectable, say, a warm 1 degree Kelvin, you would need to be accelerating at a staggering 1 quintillion times the force of gravity on Earth, a realm currently far beyond our engineering capabilities. The implications of this are nothing short of revolutionary for our understanding of physics. It blurs the line between thermodynamics and the laws of motion, suggesting that heat and acceleration are fundamentally intertwined. It forces us to accept that the concept of a particle is not an absolute truth of the universe, but a relative one dependent on the observer's path through space-time. This is a direct challenge to the way we typically think about reality, elevating the principle of relativity to the quantum realm in a way that even Einstein might have found startling. It suggests that the vacuum itself is not an empty stage but an active participant in physics, whose appearance changes dramatically depending on how you move across it. While creating the immense accelerations needed to see a warm glow of Unruh radiation is currently a fantasy, physicists are devising incredibly clever ways to look for its fingerprints. One promising avenue involves using ultra-high-intensity lasers to accelerate electrons to nearly the speed of light in just a minuscule distance, creating mind-boggling acceleration values for a fleeting instant. The idea is to see if these violently accelerated electrons interact with the quantum vacuum in a way that betrays the presence of the Unruh particles, perhaps by scattering off them or emitting a specific signature of radiation. Other proposals involve looking for the effect in the vibrations of supercooled atoms or in the peculiar dynamics of certain superconducting materials. Confirming the Unruh effect would be a monumental validation of quantum field theory in curved space-time and open a new window into the intimate and strange relationship between motion, heat, and the very nature of reality. Now, if the Unruh effect shows us that reality depends on your state of motion, our next theory proposes a connection so profound it could literally bridge the two greatest pillars of modern physics. It's called the ER equals EPR conjecture, and it suggests that the spooky, instantaneous link of quantum entanglement might have a physical shape, a microscopic wormhole threading through the fabric of space-time. To unpack this incredible idea, we need to look at its two halves. The first, EPR, comes from a famous thought experiment proposed by Einstein, Podolsky, and Rosen in 1935. They pointed out that quantum mechanics allows for what Einstein called spooky action at a distance. You can create a pair of entangled particles whose properties are intrinsically linked, no matter how far apart they are separated. Measure the spin of one particle here on Earth, and you instantly know the spin of its partner, even if it's on the other side of the galaxy. This seems to violate the cosmic speed limit set by the speed of light, and it deeply troubled Einstein. The other half, ER, refers to the Einstein-Rosen bridge proposed by Einstein and Nathan Rosen in 1935. This is the original and more formal name for what we now commonly call a wormhole, a theoretical tunnel or shortcut through the fabric of space-time that could connect two distant points. For decades, these two ideas, entanglement and wormholes, were considered completely separate. One was a bizarre quantum phenomenon with no clear mechanism, the other a speculative feature of general relativity that was thought to be too unstable to ever be traversable. The genius of the ER equals EPR conjecture, largely championed by physicists Juan Maldacena and Leonard Susskind, was to propose that these two concepts are not just similar, they are one and the same. The conjecture states that every pair of entangled particles is, in fact, connected by a microscopic Einstein-Rosen bridge. That spooky, non-local connection isn't happening across space. It's happening through a tiny, Planck-length wormhole that geometrically links them. In this view, entanglement isn't some ethereal, mathematical link. It is a physical structure woven into the geometry of the universe itself. This provides a breathtakingly elegant potential solution to the black hole information paradox. Imagine a black hole forming. According to Hawking's calculations, it should slowly evaporate, and the information about what fell into it would be lost forever, violating quantum mechanics. But if ER equals EPR is correct, the particles of Hawking radiation escaping the black hole are entangled with particles that fell inside long ago. That entanglement means they are connected by these microscopic wormholes. From the outside, the black hole looks like it's emitting random radiation, but on the inside, the information is not lost. It is preserved in the intricate web of wormholes connecting the interior to the exterior. The wormhole becomes the mechanism that saves quantum mechanics, ensuring that information can, in principle, be recovered. The implications of this go far beyond black holes. It suggests that the fabric of space-time itself might be built and held together by quantum entanglement. Think of the universe not as a static stage, but as a dynamic network of correlations. Everywhere that particles are entangled, there are these tiny, submicroscopic threads stitching space together. If you could somehow sever all the quantum entanglement between two regions, the space between them might literally cease to exist or tear apart. This provides a stunning new perspective on the holographic principle, suggesting that the entanglement between different parts of the boundary is what builds the geometry of the interior, like threads weaving a tapestry. Naturally, this is a conjecture that is still very much in the realm of theoretical exploration. We cannot yet probe these Planck-scale wormholes or directly observe the geometric structure of entanglement. However, the mathematics behind it is remarkably consistent and has become a major driving force in theoretical physics, inspiring new ways to think about quantum gravity. It represents a monumental shift in perspective, daring to propose that the deepest laws of the quantum world and the large-scale structure of the cosmos are not just compatible, but are two different descriptions of the same incredibly connected reality. It's a theory that turns the universe's most mysterious connection into its most fundamental architecture. But perhaps no single idea has forced a more dramatic confrontation between the laws of the very large and the very small than the one we explore now. This is the black hole information paradox, a puzzle so deep that it has divided physicists for decades and challenged our very understanding of reality. It all began with Stephen Hawking's stunning realization that black holes are not entirely black. He calculated that due to quantum effects near the event horizon, these cosmic monsters should slowly leak radiation and eventually evaporate, fading out of existence entirely. This Hawking radiation is thermal, a featureless glow of heat that carries energy away from the black hole, and therein lies the problem. If a black hole evaporates completely, what happens to all the information about the things that fell in? Imagine tossing a beautifully detailed book into a fire. The book burns, releasing heat and light thermal radiation, much like Hawking radiation. If you could somehow collect every single photon and ash particle from that fire, in principle, you could reverse the process and reconstruct the book. The information about its words and binding is not destroyed, it's just scrambled. Quantum mechanics is built on this unshakable principle. Information is always preserved. It can be changed, but it can never be truly erased. Hawking's calculations seem to break this fundamental law. He argued that the Hawking radiation being emitted is random and thermal. It contains no information whatsoever about the specific particles that formed the black hole or fell in later. It doesn't matter if the black hole was made from a collapsed star or a billion dictionaries. The radiation coming out would look exactly the same. Therefore, when the black hole finally evaporates, all the unique information about everything it ever consumed would be lost to the universe forever. This conclusion pitted two pillars of physics against each other: general relativity, with its prediction of Hawking radiation, and black hole evaporation, seemed to demand that information could be destroyed. Quantum mechanics, with its core principle of unitarity, insisted it could not. For decades, this was the standoff, with most physicists siding with quantum mechanics and trusting that Hawking must be missing something. The prevailing belief became that the information must somehow be encoded in the Hawking radiation, but no one could figure out how the random thermal glow could possibly hold such complex data. This led to some of the most creative and mind-bending proposals in theoretical physics. One of the most prominent is the idea of holographic storage on the event horizon. Drawing on the work of Jacob Bekenstein and Leonard Susskind, this solution suggests that when something falls into a black hole, its information isn't actually lost inside the singularity. Instead, it is instantly and perfectly encoded onto the two-dimensional surface of the event horizon, like a cosmic hologram. The three-dimensional interior of the black hole is an illusion. The true description of its contents is painted on its boundary. Then, as Hawking radiation is emitted, this radiation somehow interacts with this encoded information on the horizon, imprinting the data onto the escaping photons in an incredibly scrambled but recoverable form. From the outside, the information is never truly lost. It's just transferred from the infalling matter to the radiation in the most complex way imaginable. However, this elegant idea birthed a terrifying new paradox: the firewall. If information is stored on the horizon and slowly released, it implies that the horizon is not the smooth, empty space that general relativity predicts. For the information transfer to work, the horizon must be a seething, violent wall of high-energy particles. An astronaut crossing the event horizon wouldn't experience nothingness. They would be instantly incinerated by this energetic barrier. This violates the fundamental principle of equivalence in general relativity, which states that falling through the event horizon of a sufficiently large black hole should be a smooth and uneventful process. You can't have both the peaceful fall predicted by Einstein and the information recovery demanded by quantum mechanics. You must choose one, and both choices break a fundamental law of physics. Recent years have seen tremendous progress, largely thanks to powerful tools like the anti-de Sitter/conformal field theory correspondence, or ADS/CFT. This duality, discovered by Juan Maldacena, provides a mathematical playground where a gravitational theory in a warped space is perfectly equivalent to a quantum field theory on its boundary without gravity. By using this framework, physicists have performed calculations that strongly suggest information is indeed preserved. The key breakthrough involves calculating something called the entropy of the Hawking radiation. At first, as the black hole emits radiation, the entropy of that radiation increases, suggesting information is being lost and the radiation is random. But incredibly, the math shows that after the black hole has evaporated about halfway, its entropy begins to decrease. the radiation particles become entangled with each other in a way that allows the information to be faithfully encoded and eventually released. This crucial turning point is described by the concept of islands in the geometry of the black hole regions inside the event horizon that somehow still contribute to the information stored outside. It's a bizarre and non-intuitive result, but it points firmly toward a universe where quantum mechanics always wins. The information paradox is not yet fully solved, but the scales have tipped dramatically. The work now is to understand the mechanism, to reconcile this with a smooth event horizon, and to finally lay Hawking's terrifying ghost to rest. This isn't just an academic debate about black holes. It's a stress test for the fundamental laws of the universe, and so far, those laws are proving to be more resilient and mysterious than we ever dreamed. Yet for all its explanatory power, cosmic inflation was born from a problem. In the late 1970s, physicist Alan Guth, then a postdoctoral researcher, was wrestling with the mysteries of grand unification and the perplexing absence of magnetic monopoles, theoretical, massive particles that should have been created in abundance in the hot, dense early universe. His calculations led him to a startling realization: a peculiar state of a hypothetical scalar field, which he dubbed the inflaton field, could have a profoundly negative pressure. In the context of general relativity, negative pressure doesn't pull things together, it pushes them apart, and not just a little. This state would cause the fabric of space itself to expand at an exponential, staggering rate. Guth famously wrote in his notebook, "Spectacular realization," understanding that this mechanism could solve not just the monopole problem, but several other cosmic puzzles in one elegant stroke. This period of exponential expansion is what we now call cosmic inflation, a brief but universe-altering event that lasted perhaps only a fraction of a second, but stretched a subatomic patch of space into a volume larger than our entire observable universe. The true brilliance of inflation lies in the profound cosmic riddles it effortlessly resolves. The first is the horizon problem. If you look at the cosmic microwave background radiation arriving from opposite sides of the sky, these two regions have exactly the same temperature to within 1 part in 100,000. Yet, according to the standard Big Bang model without inflation, these regions could never have been in thermal contact. Light simply hasn't had enough time to travel between them since the beginning. It's like walking into a vast concert hall and finding that every single person, even those on opposite balconies, has the exact same body temperature without ever having communicated. Inflation solves this by proposing that these wildly separated regions were indeed once neighbors, packed into that tiny, pre-inflated patch where they easily reached a uniform temperature. The subsequent hyper-expansion then stretched them far apart, freezing that uniformity into the sky we see today. The second major puzzle is the flatness problem. Measurements of the universe's geometry show it to be remarkably flat, meaning the fabric of space-time on cosmic scales has very little overall curvature. For the universe to still be this flat after nearly 14 billion years of evolution, its initial curvature at the Big Bang would have had to be fine-tuned to an absurdly precise degree, like balancing a pencil on its tip for eternity. Any tiny deviation from perfect flatness would have been magnified over time, leading to a universe that either quickly recollapsed or expanded into a barren void. Inflation acts as a cosmic iron, relentlessly stretching space so much that any initial curvature is smoothed out to near perfection. No matter how curved your starting patch is, inflating a region by a factor of 10 to the power of 78 will make any local geometry appear flat, just as the surface of a massively inflated balloon appears flat compared to your immediate viewpoint. Perhaps most crucially, inflation doesn't just create a smooth universe, it also provides the seeds for all future structure. Due to quantum mechanics, the inflaton field wasn't perfectly uniform. It was subject to tiny, inevitable quantum fluctuations, brief, random changes in energy that flickered in and out of existence. During inflation, these microscopic quantum jitters were suddenly stretched to astronomical sizes, frozen into the fabric of space as faint ripples in density. Slightly denser regions had slightly stronger gravity, slowly pulling in more matter over billions of years. These tiny imperfections were the blueprints for everything the vast cosmic web of galaxies, clusters, and superclusters we see today. This is inflation's most spectacular prediction, that the largest structures in the universe grew from the smallest possible quantum vibrations, and we have stunningly precise confirmation of this. The pattern of hot and cold spots in the cosmic microwave background, meticulously mapped by satellites like Planck, matches the predicted spectrum of these primordial density fluctuations with breathtaking accuracy. It is the direct fingerprint of quantum mechanics written across the entire sky. The basic framework of inflation is powerful, but it has since blossomed into a family of models, each with its own fascinating implications. One compelling variant is chaotic inflation, which suggests that the inflaton field might have started with randomly high values in different parts of the pre-inflated universe. This would lead to patches inflating at different rates and for different durations, potentially creating a complex, fractal-like multiverse where each inflated region becomes its own separate universe with possibly different physical laws. This seamlessly leads to the concept of eternal inflation, where the process may have no true beginning or end. In this view, the inflaton field's decay into a stable state doesn't happen everywhere at once. It occurs in localized bubbles like nucleation in a boiling pot of water. Each bubble where inflation ends becomes a Big Bang universe like our own. But the space between these bubbles continues to inflate at an exponential rate, constantly creating more room for new bubbles to form. This suggests our entire universe may be just one bubble in an infinite, ever-growing froth of inflating space and budding universes, a truly timeless, self-reproducing multiverse. Connecting this majestic cosmic theory to the microscopic realm of quantum gravity remains one of the greatest challenges in physics. The energy scales at which inflation occurred are unimaginably high, far beyond what any particle accelerator can probe, placing it squarely at the frontier where a theory of quantum gravity is needed. String theory and loop quantum gravity both offer different perspectives on how the inflaton field might emerge from a more fundamental description of reality. Some models suggest inflation could have been initiated by a quantum tunneling event from nothing, or from a previous cosmological phase. The ultimate goal is to understand what set the inflaton field in motion in the first place, and to find any unique signatures in the cosmic microwave background or the distribution of galaxies that could point to a specific quantum gravity model. While inflation is our best story for the universe's first moment, its final chapters are still being written, waiting for a deeper theory to reveal its truest quantum origin. But if inflation paints a picture of a universe born from a single, explosive event, what if that event wasn't the beginning, but merely one chapter in an eternal cosmic story? This brings us to the grand and ancient idea of the cyclic universe, a model that suggests our cosmos is caught in an endless loop of birth, death, and rebirth. In this view, the Big Bang wasn't a unique moment of creation from nothingness, but the latest in an infinite series of transitions, a cosmic cycle where the universe expands, contracts, and explodes back into life again. It's a vision that replaces a single, linear timeline with a majestic, never-ending Ouroboros, a universe that consumes itself only to be born anew. Among the most sophisticated modern versions of this idea is the Steinhardt-Tirok model, developed by physicists Paul Steinhardt and Neil Tirok. Their framework is beautifully built upon the foundations of M-theory and the concept of a brain world that we explored earlier. Imagine our three-dimensional universe as one membrane or brain floating in a higher dimensional space. Parallel to it, just a minuscule distance away in this extra dimension, floats another three-dimensional brain, a parallel universe forever hidden from our view. In this model, the force we call dark energy is not a mysterious substance causing an endless drift into emptiness, but is instead the gentle force pulling these two brains together over trillions of years. The cyclical drama begins as these two worlds slowly accelerate toward each other through the higher dimensional bulk. When they finally collide, the immense kinetic energy of the impact is converted into a firestorm of radiation and matter, igniting a new hot Big Bang and launching a new period of expansion. Our universe isn't born from a singularity, it's born from a collision. After the bang, the brains bounce apart, and the newborn universe expands and cools, allowing galaxies, stars, and planets to form. But the pull between the brains remains, acting as that latent dark energy. After an immense epoch, the expansion is overcome, and the attraction draws the brains together once more, setting the stage for the next collision and the next cosmic cycle. This breathtaking process could have been repeating itself forever, with no beginning and no end. Another compelling cyclic model comes from physicists Loris Baum and Paul Frampton, which offers a fascinating alternative to the traditional Big Crunch. In their vision, the universe's expansion, driven by dark energy, doesn't lead to a dramatic collapse. Instead, as it expands, it eventually reaches a point of such extreme thinness that it undergoes a quantum phase transition. At this moment, the universe effectively splits in two. One part, containing all the matter and entropy, contracts but not into a singularity. The other part, an empty, smooth universe, continues expanding. From our perspective inside the cycle, we would only experience the continuous expansion of the smooth, empty part, which then seeds the next bang. This clever mechanism avoids the problematic build-up of entropy that plagued earlier cyclic models, as the entropy is effectively discarded into the contracting phase with each cycle. These cyclic theories offer profound philosophical and scientific advantages. They completely sidestep the thorny issue of the initial singularity, that point of infinite density where the laws of physics break down. There is no T=0 moment to explain. The universe has always existed in a cycle of renewal. They also provide a natural, dynamical explanation for dark energy. It's not a cosmological constant, but the force that fuels the cycle itself, the engine of cosmic rebirth. Furthermore, these models make a spectacular, testable prediction. The violent collision of brains in the Steinhardt-Turok model or the phase transition in others would generate a primordial background of gravitational waves, ripples in the fabric of space-time itself. Unlike the inflationary gravitational wave signal, which is a relic of a one-time quantum fluctuation, the cyclic model predicts a very specific spectrum and pattern of these waves, imprinted with the signature of a collision. The next generation of space-based gravitational wave observatories, like the proposed Laser Interferometer Space Antenna, or LISA, could be sensitive enough to listen for this echo of a cosmic collision, potentially providing the first direct evidence that our universe is just one in an infinite series. But if the cyclic universe offers a vision of eternal rebirth, our next theory presents a threat that is absolute and final. This is the concept of vacuum decay, a hypothesis so unsettling it suggests the entire cosmos could be annihilated in an instant, not with a bang, but with a silent, fundamental rewrite of reality itself. The idea hinges on a startling property of the universe we've already touched on, the Higgs field. This energy field that permeates all of space and gives particles their mass might not be in its most stable, lowest energy state. Instead, our universe could be resting in a false vacuum, like a ball perched precariously on the side of a valley, rather than sitting peacefully at the very bottom. It's stable for now, but it's not truly stable forever. The terrifying mechanism for change is a quantum phenomenon known as tunneling. In the quantum world, particles can occasionally perform the impossible, like passing through a solid wall, because their behavior is governed by probability. In the same way, a tiny, random quantum fluctuation in the Higgs field could, by sheer unimaginably bad luck, provide the energy needed to push that metaphorical ball over the lip of the valley and into a much, much deeper one. This wouldn't be a simple change, it would be a catastrophic phase transition. At that precise point in space, the Higgs field would drop down to its true, absolute minimum energy state, its true vacuum. The laws of physics as we know them would cease to exist in that spot. The fundamental constants, the strength of forces, the mass of electrons, would be reconfigured into something entirely new and almost certainly incompatible with life, or even with the existence of atoms as we know them. This event would create a microscopic bubble of this new, true vacuum, and this bubble would not sit still. Because the energy state inside is lower, the walls of the bubble would be under an immense negative pressure, causing them to expand outward in all directions. Critically, the expansion would not be limited by the speed of light. The bubble's wall itself would move at the speed of light. There would be no warning. One moment, everything is normal. The next, a sphere of total annihilation is rushing toward you, rewriting the fabric of reality at the speed of light. You wouldn't see it coming because the first signal of its approach would be the wall itself. The very laws of physics that allow for light, for perception, for existence, would be erased just before they reached you. The entire observable universe, every galaxy, every star, every memory, would be replaced by a new universe operating under alien and likely barren physical laws. So how likely is this cosmic doomsday? Physicists have been intensely studying the stability of the Higgs vacuum based on the mass of the Higgs boson and the mass of the top quark, the heaviest known fundamental particle. The calculations are fiendishly complex, but the current best estimates suggest a frightening possibility. Our vacuum is metastable. It's not completely unstable, destined to decay tomorrow, but it's not perfectly stable either. It's in a precarious gray zone. The ball is on a very, very shallow slope. The good news is that the predicted half-life for such a decay is astronomically long, longer than the current age of the universe by many orders of magnitude. The probability of it happening in any given volume of space in a given year is so infinitesimally small that it might as well be zero. Yet, in an infinite universe or a multiverse, even events with probability zero given enough time might eventually occur. The true terror of vacuum decay isn't that it's probable, but that it is possible. It is a reminder that the comfortable, stable reality we take for granted might be a temporary arrangement, a local valley in a much vaster and more dangerous cosmic landscape, and that the universe holds forces capable of undoing everything in the blink of an eye. From the terrifying possibility that our universe could be rewritten by vacuum decay, we turn to a theory that questions the very nature of our existence in an entirely different way. What if our reality, with all its galaxies, laws of physics, and conscious experience, isn't fundamental at all, but an artificial construction? This is the simulation hypothesis, a modern, technologically infused twist on an ancient philosophical question, which proposes that we are all living inside an immensely sophisticated computer simulation, much like a character in a video game created by a vastly more advanced civilization. The idea was rigorously formalized in 2003 by philosopher Nick Bostrom in a now famous paper. He didn't claim we are definitely in a simulation, but rather presented a fascinating trilemma, a logical argument with three possible options, only one of which can be false. He argues that at least one of the following propositions must be true. First, that almost all civilizations at our level of technological development go extinct before becoming technologically mature. Or second, that almost all technologically mature civilizations lose all interest in creating ancestor simulations, high-fidelity simulations of their forebears. Or third, that we are almost certainly living in a computer simulation. The logic is compelling. If a civilization ever reaches a stage where it can run vast numbers of these simulations, and if it has any desire to do so, then the number of simulated minds would quickly and vastly outnumber the one biological civilization that created them. Therefore, statistically speaking, any randomly selected conscious being, like you or me, is far more likely to be one of the simulated ones than the original biological one. It's a simple numbers game. Proponents of the hypothesis point to several facets of our universe that they argue are suspiciously simulation-like. The first is the breathtaking pace of our own technological advancement. In just over a century, we've gone from rudimentary mechanical calculators to creating immersive virtual realities and artificial intelligences that can beat the world's best players at complex games. If this exponential curve continues, it seems almost inevitable that a future civilization would possess the computing power to run a universe-scale simulation, complete with conscious beings inside it who are utterly unaware of their programmed nature. Secondly, they point to the fact that our universe appears to be fundamentally mathematical. The laws of physics aren't just described by math, they are math. They run on a set of immutable, computable rules, much like the code underlying a software program. At the smallest scales, reality appears to be pixelated, quantized into discrete packets of energy, space, and time, which is exactly what you would expect from a digital computation. There's even a maximum speed limit, the speed of light, which acts like a processing speed cap, preventing the simulation from overloading. Yet, for all its provocative appeal, the simulation hypothesis faces fierce criticism, primarily on the grounds of testability. Many scientists argue that it is not a scientific theory at all, but a philosophical proposition. A core tenet of science is that a theory must be falsifiable. There must be some conceivable observation that could prove it wrong. If any potential evidence against the simulation could be explained away by the programmers simply altering the code, then the idea becomes unfalsifiable and moves into the realm of metaphysics. Furthermore, the computational requirements for simulating every single particle in a universe, let alone the conscious experiences of billions of beings, are staggering, perhaps physically impossible even for an advanced civilization. It might require more atoms to build the computer than exist in our universe. Some researchers, however, are genuinely looking for potential glitches in the matrix, anomalies that could betray the simulated nature of reality. These could include precise limitations in energy measurements, unexpected errors in the constants of nature, or strange statistical fingerprints in high-energy cosmic rays. Others suggest that if the simulation uses a finite grid, there might be a detectable graininess to space-time at the very tiniest scales. While no such evidence has been found, the search itself reflects the theory's power to spark curiosity. Ultimately, whether you see it as a profound insight or a modern-day philosophical curiosity, the simulation hypothesis serves a vital purpose. It forces us to confront deep questions about consciousness, reality, and our place within the cosmos, using the language of our time to ask if the universe is, at its heart, a grand and mysterious computation. We've explored cosmic threats and simulated realities, but now let's turn to a form of matter so strange it seems to defy one of physics' most sacred principles. Imagine a clock that ticks forever without any energy input, a structure that moves perpetually, not in defiance of the laws of thermodynamics, but because of a profound nuance within them. This is the world of time crystals, a concept that sounds like it belongs in science fiction, but represents one of the most fascinating breakthroughs in modern physics. The story begins with a brilliant, speculative idea from Nobel laureate Frank Wilczek. In 2012, he asked a deceptively simple question: could there be a phase of matter that breaks time translation symmetry? We're familiar with objects that break spatial symmetry. A crystal, for example, has a structure that repeats in space, and its pattern remains even in its lowest energy state. Wilczek wondered if something could exist that also repeats in time, oscillating in a periodic cycle without consuming energy, even in its quantum ground state. This would mean the system isn't losing energy to friction or dissipation. The motion is a fundamental, unchangeable property of its existence, like a quantum heartbeat that cannot be stilled. Initial excitement was quickly met with skepticism. Many physicists argued that such a perpetual motion machine, even a quantum one, must violate the second law of thermodynamics or the principle of energy conservation. The key insight that resolved this paradox was understanding that time crystals don't create energy. They exist in a stable, non-equilibrium state where motion is locked into the system without any possibility of energy loss. They aren't engines, they are more like cosmic gears, forever turning because they are fundamentally stuck in a cycle. Turning this theoretical concept into experimental reality required immense creativity. The first successful creation of a time crystal didn't use some exotic, new material, but rather a carefully engineered system within a diamond. Researchers used a specific defect in diamond known as a nitrogen vacancy center, where a nitrogen atom sits next to a missing carbon atom in the crystal lattice. By bombarding this system with precisely tuned microwave pulses, they could force the spins of the surrounding atoms into a stable, repeating cycle of flipping that persisted long after the initial pulses stopped. This was a driven time crystal requiring a periodic kick to maintain its stability against decoherence. Even more impressive were experiments with chains of ions or superfluid circuits. In one landmark study, scientists used a chain of ytterbium ions, using lasers to arrange them in a ring and induce interactions that caused their spins to flip back and forth at a period different from the driving force. This discrete time crystal showed the hallmark signature: robust, long-lasting oscillation that was protected from perturbations by the system's own quantum many-body interactions. It was a new phase of matter, one defined not by its structure in space, but by its unwavering rhythm in time. The potential applications of this discovery are as profound as the phenomenon itself, particularly in the quest to build a practical quantum computer. The greatest challenge in quantum computing is decoherence, the tendency for qubits to lose their delicate quantum state due to tiny interactions with their environment. Time crystals, with their inherent stability and resistance to disturbance, offer a tantalizing solution. A qubit built from a time crystal's oscillating state could potentially maintain its coherence for vastly longer periods, acting as a robust quantum memory or a more stable component in a quantum circuit. Furthermore, the study of time crystals is forcing us to rewrite the textbook on thermodynamics. For centuries, thermodynamics has been the science of systems in equilibrium. Time crystals are a stark, undeniable example of a system that is inherently out of equilibrium, yet still stable and ordered. They are opening an entirely new chapter in physics, the study of non-equilibrium phases of matter, teaching us how complexity and order can emerge and persist in a universe constantly striving for disorder. They are a testament to the fact that even our most fundamental laws still hold deep, beautiful mysteries waiting to be uncovered, showing us that even in its lowest energy state, the quantum world is never truly still. But if time crystals reveal a universe that never truly rests, our next theory tackles one of the most confounding questions of all. How does our solid, objective, everyday reality even emerge from the fuzzy, probabilistic quantum world beneath it? This is the puzzle of quantum Darwinism, a fascinating theory that proposes reality isn't chosen by a conscious observer, but is instead sculpted by a process strikingly similar to natural selection. To understand why this idea is so necessary, we must revisit the infamous measurement problem. In the quantum realm, particles exist in a superposition of all possible states. An electron is both here and there, spinning up and down simultaneously. This is its wave function, yet the moment we measure it, this blur of possibilities seems to collapse into a single, definite outcome. The cat is either alive or dead. For decades, the prevailing Copenhagen interpretation treated this collapse as a fundamental, random act, a special rule that only applies upon observation. But this raises a deeply uncomfortable question. What counts as an observation? Where is the line between the quantum and classical worlds? Quantum Darwinism, developed by theorists like Worlds offers a far more elegant and continuous solution. It argues that the collapse isn't a sudden event triggered by a conscious mind. Instead, it's a gradual process of selection driven by the environment itself. The core mechanism is decoherence. Imagine a delicate quantum system like a single atom in a superposition. Now consider its environment, the countless photons of light, air molecules, and dust particles constantly bouncing off it. Each interaction is like a tiny, inadvertent measurement. These environmental particles don't care about the atom's quantum state. They simply collide with it and carry away a tiny piece of information about its position, its spin, its energy. Very quickly, the environment becomes a repository of information about the system. But here's the critical twist. Not all quantum states are created equal in this process. Some states are incredibly fragile. They are easily disrupted or decohered by these environmental interactions. Their quantum phase information is scrambled and lost to the environment almost instantly. Other states are far more robust. They can withstand these constant bombardments without being destroyed. These are the states that leave a strong, redundant imprint on the environment. It's this redundancy that is the key to objective reality. This is where the Darwinian analogy comes in. The environment acts as a selective pressure. The fragile quantum states are like poorly adapted species. They are quickly wiped out by decoherence. The robust states, however, survive and proliferate. They are copied over and over again into the environment. Thousands of photons may each carry the same information. The electron is here. This creates what is known as a pointer state, the state the system's pointer seems to settle on. Because so many independent parts of the environment now agree on this single outcome, any observer, whether a person, a camera, or a scientific instrument, will only have access to this consensus information. They will all see the same definite result. The countless other possibilities haven't vanished. They've simply become so faint and inaccessible within the environmental noise that they are effectively invisible. Reality becomes objective not because it is chosen, but because it is the state that has been most successfully broadcasted and reinforced. The implications of this for the foundations of quantum mechanics are profound. It removes the need for a special, privileged role for conscious observation, placing the quantum to classical transition firmly within the domain of standard physics. It suggests that the world we perceive is not the full quantum tapestry, but a tiny subset of it, the classical information that has survived the relentless process of environmental selection. Our reality is not the entire story. It is simply the headline that has been printed across countless environmental newspapers. This framework also provides a natural explanation for why the classical world appears the way it does. The pointer states that survive are typically those associated with familiar properties like position and momentum, precisely because these are the states that interact most predictably and redundantly with our environment. Quantum Darwinism doesn't just solve a conceptual problem. It explains the very texture of the world we experience, revealing our objective reality as the winning ticket in a constant, invisible cosmic lottery. Yet for all our searching for physical mechanisms from actions to modified gravity, we are inevitably led to a deeper, more philosophical question that underpins so many of these cosmic mysteries. Why does the universe appear so perfectly tailored for our existence? This brings us to the anthropic principle, a concept that is as profound as it is controversial, suggesting that the very laws of physics we strive to explain might be shaped by the simple, unshakable fact that we are here to observe them. The principle comes in two primary forms, each with a different level of assertiveness. The weak anthropic principle is almost a statement of logical inevitability. It simply notes that the observed values of all physical constants and cosmological quantities are not random. they must be compatible with the existence of carbon-based life that has evolved to observe them. We cannot possibly find ourselves in a universe that is incompatible with our own existence. For example, the universe is about 13.8 billion years old. That seems like a random number, but it isn't. It takes about that long for generations of stars to live, die in supernova, and forge the heavy elements like carbon and oxygen that are essential for planets and life. A universe that was only 1 million years old wouldn't have any observers, so of course we don't find ourselves in one. The weak principle is a selection effect, a cosmic version of the observation that a puddle might be amazed at how perfectly the hole it sits in fits its shape. Then there is the strong anthropic principle, which takes a much more dramatic stance. It proposes that the universe must have those properties that allow life to develop within it at some stage in its history. This version moves from a simple observation about our local conditions to a statement about a necessary law of the universe. It hints that there is something fundamentally special or required about the emergence of consciousness in the cosmos, though it carefully avoids specifying any divine or purposeful cause. Where this principle truly shines is in addressing the staggering problem of fine-tuning. So many of the fundamental constants of nature seem precariously balanced. If the strong nuclear force were just a few % stronger, all the hydrogen in the early universe would have fused into heavier elements, leaving no fuel for stars. If it was slightly weaker, heavy elements necessary for planets and life would never form. If the gravitational constant were a little stronger, the universe would have collapsed back on itself long before life could arise, a little weaker, and matter would never have clumped into galaxies and stars. The list of these cosmic coincidences is long and deeply unsettling to physicists who believe the laws of nature should be elegant and necessary. The anthropic principle offers a powerful, if disquieting, explanation. The constants are what they are because if they were any different, we wouldn't be here to talk about it. However, this very strength is also the source of its fiercest criticism. Many scientists argue that the anthropic principle is a conversation stopper, not a predictive scientific tool. It can be used to explain almost any observation after the fact, but it doesn't allow us to predict anything new or point us toward new physics. It can feel like a retreat from the traditional goal of science, which is to find mechanistic, causal explanations for why the universe is the way it is. This is where the principle finds its most potent modern application, as the essential interpretive key for the multiverse. If there is only one universe, the bizarre fine-tuning seems like an incredible mystery. But if eternal inflation or string theory's landscape is correct, and there are a near infinite number of universes, each with its own randomly selected set of physical constants, then the mystery evaporates. In most of these universes, the constants will be wrong. They will be stillborn, collapsing instantly or expanding into empty voids. But in a tiny, unimaginably small fraction of them, the dice roll will be just right. Life will emerge, and observers will marvel at how perfectly tuned their universe is, never realizing they have simply won the ultimate cosmic lottery. The anthropic principle becomes the bridge that connects a vast, impersonal multiverse to our own specific, life-friendly reality. It directly addresses puzzles like the cosmological constant problem, suggesting that the value we observe isn't fine-tuned by design, but is simply the only value that allows for galaxies and life to form in our particular bubble. To truly grasp the weight of this idea, consider a simple thought experiment. Imagine a universe where the electromagnetic force is significantly stronger. Atoms would be smaller and chemical bonds would be tighter, likely preventing the complex carbon chemistry that is the basis for life as we know it. Now imagine a universe where dark energy is 100 times more powerful than in our own. The accelerated expansion would have begun immediately after the Big Bang, tearing apart any potential galaxies before they could even form. In such a place, the sky would be utterly black and empty, with no stars, no planets, and certainly no one to look up and wonder why. The anthropic principle doesn't tell us why these constants have the values they do in an absolute sense. Instead, it tells us that our observation of them is inextricably linked to our own existence, framing our entire search for fundamental laws within the context of the one universe we are privileged, or perhaps fated, to inhabit. And yet, even as we step back to consider our place in a possibly fine-tuned cosmos, our most powerful theories are being challenged by the quietest particles in existence. For decades, the standard model of particle physics stood as a near-perfect cathedral of knowledge, predicting the behavior of subatomic particles with breathtaking precision. But this elegant structure has a crack in its foundation, and it was discovered not by smashing particles together at incredible speeds, but by watching ghostly particles from the sun change their identity on the fly. This is the mystery of neutrino oscillations, and it's a clue that the universe is hiding secrets even more profound than we imagined. Neutrinos are the universe's most elusive spectators. Trillions of them pass through your body every second, mostly from the sun, and they do so without a single interaction. They were long thought to be massless like photons and to come in three immutable flavors: the electron neutrino, the muon neutrino, and the tau neutrino. But experiments deep underground began to tell a different story. Detectors like Super Kamiok and in Japan and the Sudbury Neutrino Observatory in Canada were built to catch these phantoms. They found something astonishing. The number of electron neutrinos arriving from the sun was only about a third of what solar models predicted. It wasn't that the sun was producing fewer neutrinos, it was that the neutrinos were changing or oscillating between their three flavors on their journey to Earth. An electron neutrino leaving the sun might arrive at Earth as a muon or tau neutrino, invisible to detectors tuned for electrons. This simple act of changing costume has a monumental implication. For neutrino oscillation to be possible, these particles must have mass, however tiny. It's a subtle point of quantum mechanics. A massless particle, like light, always travels at the speed of light and experiences no time. For it, the journey from the sun to Earth is instantaneous, but if a particle has mass, it must travel slower than light, and time passes for it. This passage of time is essential for the oscillation process to occur. The discovery that neutrinos oscillate, which earned the 2015 Nobel Prize in Physics, was a direct, undeniable proof that neutrinos have mass. This single fact shatters the pristine perfection of the Standard Model, which explicitly predicted that neutrinos should be massless. We now have definitive evidence that our most complete theory of the physical world is incomplete. There must be new physics, a deeper layer of reality beyond the Standard Model, to explain why these ghosts weigh anything at all. The immediate question is, how do they get this mass? Their masses are almost incomprehensibly small. The heaviest neutrino is at least 10 million times lighter than an electron. One compelling explanation is the seesaw mechanism. This elegant idea posits that for every light, familiar neutrino we know, there exists a hypothetical, incredibly heavy partner, a sterile neutrino. The term sterile means it wouldn't interact through any of the known forces except gravity. It would be even more ghostly than its regular counterpart. In this model, the reason our known neutrinos are so light is because their immense sterile partners are acting like an anchor on a seesaw. As the mass of the heavy sterile neutrino goes up, the mass of the light standard neutrino is pushed down. This mechanism not only explains the baffling smallness of neutrino masses, but also provides a perfect candidate for dark matter. A sterile neutrino, if it exists, would be stable, neutral, and would only interact gravitationally, checking every box for a dark matter particle. This is why the study of neutrinos has exploded into one of the most active frontiers in physics. Major international experiments are now dedicated to pinning down their properties. The Deep Underground Neutrino Experiment, or DUNE, is at the forefront. It will fire a powerful beam of neutrinos from the Fermilab facility in Illinois straight through 800 miles of the Earth's crust to a massive liquid argon detector housed a mile underground in South Dakota. This incredible baseline will allow scientists to observe neutrino oscillations with unparalleled precision. One of their primary goals is to investigate a potential difference in the behavior of neutrinos and their antimatter counterparts, antineutrinos. This difference, known as CP violation, could be the key to understanding one of the universe's great origin mysteries: why, after the Big Bang, matter overwhelmingly survived over antimatter. If a significant CP violation is found in neutrinos, it could reveal the mechanism that tipped the primordial scales, allowing for the existence of everything we see today: galaxies, stars, planets, and us. The pursuit of these questions transforms abstract theory into tangible, cutting-edge engineering. DUNE FAR detector will be filled with 70,000 tons of liquid argon, kept at -186 degrees Celsius, to capture the precise moment a neutrino interacts and creates a shower of other particles. Other experiments, like the upcoming Juno Observatory in China, will use 20,000 tons of liquid scintillator to measure the energy spectrum of neutrinos with extreme accuracy, helping to determine the exact ordering of the three neutrino masses. This global effort highlights a profound shift in particle physics. We are no longer just building bigger colliders to find heavier particles. We are also building more sensitive detectors to study the lightest ones, understanding that their subtle quantum dances might hold the answers to the universe's biggest questions. The humble neutrino, once thought to be a mere footnote in the subatomic world, has become our most promising guide into the vast, uncharted territory beyond the standard model. But perhaps no single idea has forced a more dramatic confrontation between the laws of the very large and the very small than the one we explore now. This is the black hole information paradox, a puzzle so deep that it has divided physicists for decades and challenged our very understanding of reality. It all began with Stephen Hawking's stunning realization that black holes are not entirely black. He calculated that due to quantum effects near the event horizon, these cosmic monsters should slowly leak radiation and eventually evaporate, fading out of existence entirely. This Hawking radiation is thermal, a featureless glow of heat that carries energy away from the black hole, and therein lies the problem. If a black hole evaporates completely, what happens to all the information about the things that fell in? Imagine tossing a beautifully detailed book into a fire. The book burns, releasing heat and light thermal radiation, much like Hawking radiation. If you could somehow collect every single photon and ash particle from that fire, in principle, you could reverse the process and reconstruct the book. The information about its words and binding is not destroyed, it's just scrambled. Quantum mechanics is built on this unshakable principle. Information is always preserved. It can be changed, but it can never be truly erased. Hawking's calculations seem to break this fundamental law. He argued that the Hawking radiation being emitted is random and thermal. It contains no information whatsoever about the specific particles that formed the black hole or fell in later. It doesn't matter if the black hole was made from a collapsed star or a billion dictionaries. The radiation coming out would look exactly the same. Therefore, when the black hole finally evaporates, all the unique information about everything it ever consumed would be lost to the universe forever. This conclusion pitted two pillars of physics against each other: general relativity, with its prediction of Hawking radiation, and black hole evaporation, seemed to demand that information could be destroyed. Quantum mechanics, with its core principle of unitarity, insisted it could not. For decades, this was the standoff, with most physicists siding with quantum mechanics and trusting that Hawking must be missing something. The prevailing belief became that the information must somehow be encoded in the Hawking radiation, but no one could figure out how the random thermal glow could possibly hold such complex data. This led to some of the most creative and mind-bending proposals in theoretical physics. One of the most prominent is the idea of holographic storage on the event horizon. Drawing on the work of Jacob Bekenstein and Leonard Susskind, this solution suggests that when something falls into a black hole, its information isn't actually lost inside the singularity. Instead, it is instantly and perfectly encoded onto the two-dimensional surface of the event horizon, like a cosmic hologram. The three-dimensional interior of the black hole is an illusion. The true description of its contents is painted on its boundary. Then, as Hawking radiation is emitted, this radiation somehow interacts with this encoded information on the horizon, imprinting the data onto the escaping photons in an incredibly scrambled but recoverable form. From the outside, the information is never truly lost. It's just transferred from the infalling matter to the radiation in the most complex way imaginable. However, this elegant idea birthed a terrifying new paradox, the firewall. If information is stored on the horizon and slowly released, it implies that the horizon is not the smooth, empty space that general relativity predicts. For the information transfer to work, the horizon must be a seething, violent wall of high-energy particles. An astronaut crossing the event horizon wouldn't experience nothingness. They would be instantly incinerated by this energetic barrier. This violates the fundamental principle of equivalence in general relativity, which states that falling through the event horizon of a sufficiently large black hole should be a smooth and uneventful process. You can't have both the peaceful fall predicted by Einstein and the information recovery demanded by quantum mechanics. You must choose one, and both choices break a fundamental law of physics. Recent years have seen tremendous progress, largely thanks to powerful tools like the anti-de Sitter/conformal field theory correspondence, or ADS/CFT. This duality, discovered by Juan Maldacena, provides a mathematical playground where a gravitational theory in a warped space is perfectly equivalent to a quantum field theory on its boundary without gravity. By using this framework, physicists have performed calculations that strongly suggest information is indeed preserved. The key breakthrough involves calculating something called the entropy of the Hawking radiation. At first, as the black hole emits radiation, the entropy of that radiation increases, suggesting information is being lost and the radiation is random. But incredibly, the math shows that after the black hole has evaporated about halfway, its entropy begins to decrease. The radiation particles become entangled with each other in a way that allows the information to be faithfully encoded and eventually released. This crucial turning point is described by the concept of islands in the geometry of the black hole regions inside the event horizon that somehow still contribute to the information stored outside. It's a bizarre and non-intuitive result, but it points firmly toward a universe where quantum mechanics always wins. The information paradox is not yet fully solved, but the scales have tipped dramatically. The work now is to understand the mechanism, to reconcile this with a smooth event horizon, and to finally lay Hawking's terrifying ghost to rest. This isn't just an academic debate about black holes. It's a stress test for the fundamental laws of the universe, and so far, those laws are proving to be more resilient and mysterious than we ever dreamed. We arrive now at our final destination, a theory so audacious it places the human mind itself at the very center of the cosmic machinery. This is the idea that consciousness causes collapse, a speculative interpretation of quantum mechanics that suggests the act of observation isn't just a passive measurement, but the very trigger that forces the quantum world to make up its mind. The roots of this idea stretch back to the pioneers of quantum theory. In the 1930s, brilliant minds like John von Neumann and later Eugene Wigner wrestled with the infamous measurement problem. If a particle exists in a blurry superposition of all possible states, what exactly causes this probability wave to collapse into a single, definite reality? The mathematics of quantum mechanics offered no clear answer. Von Neumann's meticulous work showed that the chain of measurement from the quantum system to the measuring device to the human eye and brain could be described as one long, continuous quantum process. He could find no special point where the collapse objectively happened. This led him, and Wigner after him, to a startling conclusion. The only thing that isn't governed by quantum rules is consciousness itself. They proposed that the human mind, through the act of observation, is the ultimate agency that completes the measurement, collapsing the wave function and actualizing reality from a sea of possibilities. This perspective creates a breathtaking, if unsettling, bridge between the material world and the world of mind. It suggests that the solid, objective universe we perceive doesn't exist in a definite state independent of us. Instead, it remains in a ghostly, suspended animation of potentialities until a conscious observer interacts with it and brings it into concrete existence. In this view, the moon is not there when no one is looking. It exists in a smeared-out probability cloud until a conscious being, whether an astronaut, a groundhog, or a curious child, glances up and crystallizes its reality. It's a concept that elevates consciousness from a passive byproduct of brain chemistry to an active participant in the creation of the cosmos, weaving the observer and the observed into an inseparable whole. Naturally, such a radical proposal faces immense criticism from the mainstream physics community. The primary objection is that it places a special role on conscious observers, creating a bizarre hierarchy of existence. Does a mouse cause a collapse? What about a bacterium or a sophisticated AI? The theory provides no clear boundary, leading to logical paradoxes. Furthermore, it seems to fly in the face of the principle of parsimony, also known as Occam's razor. Invoking a mysterious, non-physical consciousness to solve a physics problem feels like introducing a far more complex element than the puzzle it aims to solve. Critics argue that it's a retreat into mysticism, abandoning the search for a physical mechanism in favor of a philosophical deus ex machina. The success of other interpretations, like the many worlds theory or the ongoing progress with decoherence, which explains the appearance of collapse through environmental interaction, has made the consciousness causes collapse idea a distinctly fringe view in modern physics. Despite its controversial status, the idea has evolved and inspired modern variants. Some researchers exploring the hard problem of consciousness, why we have subjective experience at all, have looked for potential quantum processes within the brain, such as in microtubules, that could somehow interact with the wave function. The hope is to find a physical basis for this interaction, grounding it in biology rather than philosophy. Experimental tests, however, are notoriously difficult to design. How do you create a controlled experiment to prove that consciousness itself is the causal agent, separate from any physical interaction? Some proposed experiments involve placing a human observer in a quantum superposition state, perhaps using a futuristic version of a Schrödinger's cat experiment, but the technological and ethical barriers are currently insurmountable. For now, the theory remains largely in the realm of metaphysical speculation, a fascinating thought experiment that challenges our deepest assumptions about reality and our place within it. It stands as a testament to the enduring mystery of quantum mechanics, a puzzle that continues to force us to question not just the nature of the universe, but the nature of ourselves. From the ghostly whispers of actions to the cosmic symphony of vibrating strings, we've journeyed through a landscape of ideas so vast and varied it defies simple summary. We've seen gravity reimagined not as a fundamental force, but as an emergent illusion born from the universe's information content. We've considered the possibility that our entire cosmos is a holographic projection, a simulation running on a computer built by an advanced civilization, or just one bubble in an infinite, frothing multiverse. Some theories, like cosmic inflation, are supported by a wealth of observational evidence and form the bedrock of modern cosmology. Others, like the consciousness causes, collapse interpretation, remain deeply speculative thought experiments that push the boundaries of science and philosophy. Yet each one, in its own way, represents a profound human attempt to peek behind the curtain of reality, to understand the hidden forces that truly govern everything from the spin of an electron to the fate of the cosmos. What ties these 30 theories together is their collective power to completely reshape our understanding of existence. They force us to confront the unsettling truth that our everyday experience of reality is a thin veneer, a simplified user interface for a far stranger and more complex underlying truth. Dark matter and dark energy are not just placeholder names for things we haven't found yet. They are clues that our theories of gravity and matter are incomplete. The bizarre behavior of quantum particles isn't just a quirk of the tiny world. It might be the fundamental mechanism that builds space-time itself through entanglement. The search for these hidden forces is more than a scientific endeavor. It's a fundamental re-examination of what is real, what is possible, and what our place is in this grand, mysterious cosmos. This isn't just an academic exercise happening in isolated lecture halls. Right now, the biggest questions in physics are being pursued with incredible ingenuity and cutting-edge technology. The Large Hadron Collider continues its search for supersymmetry and extra dimensions by smashing protons together at nearly the speed of light. Gravitational wave observatories like LIGO and Virgo are listening to the reverberations of black hole mergers, probing the nature of gravity itself. Deep underground, detectors filled with liquid xenon or argon are waiting for the faintest bump from a dark matter particle. In laboratories around the world, scientists are creating new states of matter like time crystals and probing the quantum realm with ever greater precision. Each new data point, each unexpected signal, has the potential to validate one of these wild theories and instantly relegate others to the history books. The journey to understand the universe's hidden forces is the greatest detective story ever told, and we are all living through its most exciting chapters. So we want to hear from you. After this tour of cosmic possibilities, which theory completely rewired your brain? Was it the holographic principle that suggests you might be a projection? The many worlds interpretation that promises another version of you made every possible choice, or something else entirely? Let us know in the comments below which idea blew your mind the most. If you enjoyed this deep dive into the edges of understanding, make sure to subscribe and hit the notification bell so you don't miss our next exploration into life's biggest mysteries. The universe is whispering its secrets, and the conversation is just getting started.